Hello everyone and welcome again to Dev Swarm October 2022. My name is Piers Ridyard. I am the CEO of RDX Works, which is a core developer of the decentralized finance protocol Radix, a public ledger entirely focused on bringing DeFi into the mainstream. Today we've got an awesome event. We're going to be looking at NFTs and whether or not they're expensive JPEGs or the future of finance, and a full Scrypto Developer Workshop. It's going to be awesome. I'm basically just going to give you guys a bit of an overview about what RDX Works and the Radix network is all about, and a bit more of a sort of a vision piece about why we think this space is exciting and why it's important. But first, before we get into that, let me just give everyone who is here physically a welcome and say a huge thank you for turning up today. That's a big part of getting on the next steps of learning how to build with this technology. A huge shout out to Lisbon, a huge shout out to Szeged, a huge shout out to Budapest, a huge shout out to Debrecen, a huge shout out to Warsaw, a huge shout out to Prague, and a huge shout out to Amsterdam. So happy you guys are all here at the same time, all working on this awesome technology. And after today, I would really encourage all of you to join our Discord community if you're not already part of it. There's a huge number of developers on the Discord channel who are very willing and able and want to help you guys get on the next stage of your journey. So if you find what you see today interesting, I strongly recommend that because it's an awesome community and a great place to learn and just hone your skills. So let's start with this simple question, which is, why do we build? And I think this is a question that sort of everyone should ask themselves when they're doing something, and it can be for fun. Like, that's absolutely and completely a legitimate reason. For RDX Works, we build because we think that finance today fails users in 1,000 different ways. And finance is actually a lot broader a concept than most people think about it. Like, at the moment, we don't think of, when you go and play World of Warcraft, the assets that you get in those games as being financial assets, or when you go and play, if you get really good at Fortnite and you get a bunch of skins, you think about buying those skins and those skins being valuable, but you don't really think of them as assets. They actually are. Like, finance is much more broadly than the stuffy sort of concept that generally people think about it as their boring relationship with their bank, which sucks for most people. The banking relationships, stock relationships, all of that financial stuff. But actually, finance is just much more broadly about the assets and objects that we as humans value and the way in which those are transacted and moved around the world. And right now, that also is, it sort of sucks and completely fails users in 1,000 different ways. So our vision is a radically better financial system, one that really is a digital first approach, one that really does take assets and the things that we own and think of as ours into the sort of into the digital age. Like, the internet has brought information, and we sort of like kicking and screaming, dragging all of these things, and we're seeing the first ideas of when you unleash a creator economy, what kind of value can actually be unlocked by that, with things like, the simple ideas of things like Bored Apes, much more to the much more complicated things that are now starting to come out with the metaverse and stuff like that. So what is that going to look like? What's a radically better financial system going to look like? Well, we believe that decentralized finance is going to eat traditional finance, that all areas of human endeavor, of GDP of countries, the way in which nations trade with each other, all of that is going to be eaten by decentralized finance, and specifically financial products and assets that are built on top of public ledgers. And when the way that I really define decentralized finance is these products and assets are built on top of decentralized ledgers, giving them a bunch of superpowers that they wouldn't have otherwise. Right now, finance can be kind of thought about like a badly connected archipelago of islands, and the way in which all of these things talk to each other makes it incredibly difficult for us to really get a full view of what our financial universe is, or indeed actually get a full view of those things that are actually valuable within our financial universe. Many of things we don't even think of as valuable today, but I think this unlocking of the creator economy and this next step with NFTs and this financialization that is now made possible with this technology of things that previously we thought of as like skill-based games or as status-based games are now going to more and more be able to be built into things that can actually be capitalized on as well. So why? DeFi is finance built for the internet age. we need a financial system that actually supports programmability, that actually supports a developer-first approach. And that is not true today. It's very difficult to build anything financial in the traditional space and requires many, many years and huge amounts of funding. Whereas in DeFi and in the NFT space, we are seeing people turn things around, in weeks. And that was reminiscent of what happened in the early ages of the internet as well. We are again at the cusp of a cutting edge technology that allows us to do things that were not possible before and start businesses that would previously be only the purview of huge companies or huge industries. DeFi can do everything that traditional finance can do today, faster, cheaper, and more efficiently. And that was the same thing that the internet did. It basically allowed people to make it easier to send information around the world, made it easier for anyone to set up shop and be able to sell services globally. It created this thing around the concept of creating digital-only businesses that just didn't really exist before. And when that happens, when we get to the point where we can unlock that power for everyone, anyone with a computer and an ability to program to be able to come on this and start building their own sort of next generation of businesses and services that need to come on top of these decentralized financial ledgers, billions of people are going to be better off as a result of that. You're going to be able to unlock liquidity. You're going to be able to give people optionality on their money and give them better ways in which they can secure their future than that you can now. So that's all cool. And, I'm sure lots of you have heard that pitch before around what is possible with a public ledger. So how is RDX Works going to make sure that that happens? And then there's sort of two parts to this. The first is what our mission is, right? What we are doing to do that. And our mission is to give builders everything they need to obsolete traditional finance. This really does concentrate on the idea that our vision here is about enabling the success of others. It's about giving the tools that are necessary for other people to be successful building on top of these platforms. We are completely focused on the user experience, the developer experience, and what tools are actually necessary to unlock all of that potential. And so our mission ultimately is to empower you, the people who are thinking about building using this technology, and empower you to be successful in doing so. Now, when a lot of people think about decentralized finance, obviously the market has changed a little bit since DeFi summer in June of before June of 2022. But what DeFi now, a lot of people think of it as this huge industry. At peak it had $200 billion under management. But actually, if you zoom out, and you can add NFTs to that, and that will probably add you another $50 million to that. But ultimately, it's actually a drop in the bucket of what 100x from here would look like. 100x from here might look like 100 trillion, like $1 trillion. And the global financial system is currently $400 trillion. And that's not just what you think of as stocks and shares and bonds and debt. That's big parts of it. But it's also things like IP and music rights and all of the kind of things that and land rights and things like the ownership of game assets, as in the entire game. Like all of these things are part of this financial picture. And so we are a very long way, we're an invisible dot on an invisible dot from where this is going to be, which is, to me, incredibly exciting. It just points to the way in which the future is going to be so exciting for what's coming and all of the potential that's there. So in 2 years, capital in the DeFi space 220x'd from $1 billion to $220 billion. But developers only 2x'd. They went from they basically went from 10,000 to 19,000 developers. That's smart contract developers, which is kind of crazy. 220x increase in developers in capital, and only a 2x increase in developers, which we thought was kind of crazy. We thought was kind of interesting, and that sort of at its peak made one developer worth $11.5 million per developer in terms of total value locked, in terms of the value that they were able to bring on average to the applications that we're building, which is a breathtaking amount of money and a huge amount of possibility that sort of exists in this space. So this sort of like next begs the question is like, why should you build? Question I was asking at the top. And also, what should you build? And these two things are only things that can actually come from experimentation and play. You don't get there immediately from just going today, you're going to go, some of you might know what you want to build, but a number of you are going to be like, I need to learn, I need to play, and that's fine. Like, exploration is really important. I'm actually going to tell you a story about exploration in the space. And what should you build? What should you build is also critical. Let me tell you a story about Hayden Adams. On July the 6th, 2017, Hayden Adams was laid off from his job. From July to October 2017, he learned to code Solidity badly. So he'd never coded before in his life. He was actually a mechanical engineer, and he started to code Solidity. In October to November, 3 months, he built the Uniswap V0 proof of concept. It took him 3 months with Solidity to get started. And this is what the first version of Uniswap looked like. From November 2017 to November 2018, Uniswap V1 was made production ready. And incidentally, that's a really long period of time, 3 months to build a prototype, but then it took him another year to build it into a production piece of code. And he actually didn't change any of the underlying functionality. It just took that long with Solidity to make a production system. And this is actually exactly why we built Scrypto and what you're going to learn about today. Scrypto is this programming language that we saw this huge need in the market for, because fundamentally, without Scrypto, it is so difficult to build production level applications. It's easy to hack something together, but when you want it to be secure and you don't want people's money to get stolen, building with a tool set that was actually designed to make what you build secure is critical to actually being able to use this technology in a way that isn't terrifying. November 2018, Uniswap started with $34,000 of liquidity. November 2019, year later, it had $20 million of liquidity at 588x. And this is going off something that basically one person built. Then by November 2020, it had $3 billion of liquidity. That's 150x. And then November 2021, $10 billion, another 3x. So what are the lessons to take away from this? 1, a person with no coding experience can build something incredible. 2, getting started by learning is the first step, and you are doing that here today. You are on your journey to learning what these tools mean and how you can think about what you can build in the space. And 3, the founder of the first $10 billion dApp on Radix might be in this room, or might be in one of the rooms that are currently happening all across Europe right now. The journey of 1,000 miles starts with the first step. And as I say, you are taking that today. That's a really important moment. And I really hope that you enjoy this first step. And what I would encourage is keep the people that you have here around you. Make sure you join the communities and go on this learning journey. Explore. It's fine if you don't know exactly what you want to do after the end of today. The important thing is you just keep walking until you find that thing that you love, that you have passion with. So thank you very much for listening to me. And now I'm going to hand you over to the team for the next phase of the introductions.
Hey, I'm Redfoo from the band LMFAO. Party rock! And I've been coding for about 5 years, and I'm obsessed.
Tell us about your first contact with crypto.
My first contact with crypto was basically the Ethereum blockchain. I had heard about Bitcoin, and I think I saw something like the Crypto Kitties. It was around that time, and I really just got into a little bit of trading it because the exchanges were open 24 hours. And got into a little bit of the Coinbase, and yeah, that was my first experience. And I started right away coding in Solidity.
What was that experience like?
it was amazing coding and solidity, coding in solidity, and discovering the whole crypto world, the blockchain world was very exciting. There was a lot of tutorials. I learned how to code a lot from the solidity, the simplicity of there's an owner and there's you have an account balance, and I learned a little bit of like fintech, the ideas of all that stuff, and it was just a whole culture that wanted to make a difference in the monetary system, and try to figure out a way to yeah, as an artist, I loved it because there was a lot of things I was doing in the world where other people would get paid for them, but we weren't getting paid. Like on Instagram, we would have all these viewers and likes and stuff, and we weren't getting paid. And YouTube was one of the first platforms that started paying. And there's always this idea, if you create a meme and all that stuff, you know, is there a way for you to get paid during the lifetime of a meme? And that invention still hasn't been made, but the NFT is the closest thing to that. I just feel like the whole crypto blockchain world is very empowering for the small guy, the little guy, you know, or girl or gal, or the little person, but you know, not the little, but the you know, but the thing is when I say little and I say small, I'm only talking about body height. I ain't talking about the other stuff. Just to let everybody know out there, because you know the package is you know, they call me FedEx. You know, it's very deliverable. It's very but not bite size. It's not bite size.
So would you call yourself a crypto believer?
Yeah, I would call myself a crypto believer, a blockchain believer, because I understand development. I understand coding. It's not a phase or a fad. It's actually an infrastructure. It's a technological platform and infrastructure where real things are being built.
Tell us about your first contact with crypto.
First contact with crypto came through coding, and thought it was amazing. The potential was incredible. Started digging, started learning, researching, and really started to understand and believe that this is a very powerful technological invention, where you can build upon, you know, you can build apps on top, dApps, decentralized and all that stuff. And I feel like for the creative community and for humanity as a whole, it's open source. It's people are trading ideas back and forth, and it's very empowering, and I believe will be the future technology. This cryptology mixed in with the ledger that never deletes. It's a write. You're writing once. You're appending, right? There's no deleting, you know, so you can see everything, and that's what's very exciting.
Tell me about your first contact with Radix.
Oh yeah, first contact with Radix, Austin, South by Southwest. I saw a computer with some code, and I was very interested, and I asked, what is that, you know? And they said, this is Scrypto. And I said, Scrypto? That's an incredible name. I said, what is it? What is we do? It's the smart contract language for Radix, and it's fast, it's safe, and it gets the developers creating NFTs in a flash and tokens, and it's for DeFi. And you know, and then you said, well, and then Piers said, you know, you can make your own swap. you can make your own DeFi, the foo swap or something, you know, right away. And I said, wow, okay. And so that's how I got introduced. And that night, I think I went and did a little tutorial on it and built a coin and had a supply of 1 million. And I was like, oh, this is great.
Hey, I'm Brian. You may have seen me around Discord as Motosharpley or DevPath. You've seen some of the YouTube videos. Um, I'm a developer who has been programming since screens were nothing more than green pixels. I was there for Web 1.0 when the proper way to make complex layouts was tables. I was there for Web 2.0 when we got JavaScript and started having interaction. Back when PHP was cool, I was part of building one of the first WYSIWYG e-commerce platforms. I dove into Web 3 with Ethereum and smart contracts, which I quickly saw a lot of extraordinary pitfalls in the ecosystem, but decided to press on in hopes that projects like Open Zeppelin could maybe tame the waters a bit. I've been programming for roughly 35 years, with probably about 25 of those being in a professional capacity. I'm pretty sure I don't even remember all the languages I've learned over the years. I've always been drawn to cutting edge tech, which leads to learning a lot. To summarize a bit though, I started with BASIC as a kid, just programming. You program pixel coordinates to animate things on screen, really. I remember it was awesome when you got the little T-Rex to walk across the screen chomping. That was considered a game at that time. Fast forward a bit, and I worked with DOS, probably around the same time, Windows 3.1 was new and exciting. When the internet first opened up to the public, I was quick to jump in and learn HTML. I used to go to the bookstores and sit for hours reading the huge programming books. Look like a giant phone book. Roll up to recent history, and I've worked on everything from PHP, Flash, and ActionScript. Went pretty heavy into Rails for a while. After Rails, I kind of moved on to Node.js ecosystem. Currently, I'd probably say TypeScript and C#.net would be kind of my go-to languages. And of course I learned Solidity with Ethereum, but really right now, all I want to do is focus on Rust and Scrypto. I've done a lot of work in point of sale, e-commerce, merchant processing, and gift cards. I also branched out and learned to program LED drivers and solar charge controllers and lighting controllers when I was working on my portable solar light towers, which I ended up receiving 2 patents for. So my first public-facing project was early in the days of the web. I was working as a chef around that time, and so a fellow chef and I jumped in and we built clubdinner.com. It was a recipe subscription site. So jump ahead a bit more, and I was working on point of sale when e-commerce became a word. So I jumped in, and that's when I got to work on one of the first GUI-based e-commerce site builder platforms. It was targeted at small to medium businesses to help them get their brick and mortar business online to compete with the new online retailers. In the process, we kind of found a niche at that time, as people were getting their business online, they were operating essentially 2 checkout systems, two inventory systems was the real problem. So, they've got one inventory, and on the one hand, they're brick and mortar systems managing that, and then they're trying to sync up what they're selling online with an inventory system online. And so we did fairly well writing some middleware in between to help small businesses navigate that. We were using things like PHP and .NET. We were a Microsoft point of sale reseller. So at the beginning of the gift card industry, we were actually one of the first companies to integrate our gift card system with Payment Tech, which is one of the largest merchant processing banks. Then I jumped over to a project where we were building a self-checkout and a mobile ordering system for these super automatic espresso machines. They grind the beans and froth your milk and everything, make your cappuccino fully automated. So we wrote programs to kind of interface with the point of sale, and you could just walk up and scan a QR code on your phone at the coffee machine, and it would brew your prepaid coffee fresh for you. So that was fun. Got to drink a lot of really good espresso. When I got done with that, I moved into progressive web apps and really kind of dove into the hybrid tech stacks, because I just really saw where, I'd already seen where desktop software, we used to load CDs and everything went software as a service and web-based. And I really believe that mobile will eventually kind of have that same progression in terms of, as this hybridization syncs up, we'll get to where we just build web apps and they work natively, desktop, mobile, Apple, Android, it doesn't matter. Everything will be a web app, and we're not far from that already. So I kind of really dove into that. Along the way, I've always been kind of keeping my eye on crypto. I looked into mining Bitcoin early on. Hell, I had a solar company at the time. I probably could have done okay, but I immediately saw a flaw in a system that continuously needs to consume more and more to produce the same end result for the same task. So I kind of kept my distance, just focused on my solar light towers, and that was that. I kind of been watching from the sidelines since Bitcoin first came out, really looking for the crypto foundation, the ecosystem to be ready for a real financial revolution. I've been a believer for really a long time, from the beginning, that if we make it easy for people to spend crypto on real tangible goods, fiat currency will be nothing more than the worthless paper it's printed on. It'll be a small flash in history looking back at how fast an open market can produce a better financial instruments than a bureaucratic, manipulated system that really was pretty much rigged by design from day one. With my background in point of sale and e-commerce, I've seen this type of transition before. And, if you think about how prolific the electronic payments are today compared to cash, just over the last 30 years, we've already seen the swap happen. With the advent of gift cards, we saw the power of tokenized currency storage and transactions. If you think about it, gift cards were really the first tokenized, trustless form of electronic payments we'd seen. At the core, it's not actually all that different from crypto. The only problem being is that it's still forced through that same little straw, that same bottleneck that has been manipulating our global financial system for ages. So, when Ethereum rolled out, I was still casually watching from the sidelines. But once the power of smart contracts clicked in my brain, I jumped in and started learning to see what could be done. I dove pretty deep into thinking maybe it was finally time to build a new financial system. And with a ton of work, it could be done to an extent. However, as we've seen, there's still some pretty extreme pitfalls, and ultimately scale would hit its limits in time as well, which we're already starting to see as well there. Nonetheless, I started mapping out a series of marketplace platform projects because fact of the matter, if you give people the ability to buy everyday items with crypto, fiat will fall. You know, I actually stumbled on Scrypto, onto Radix and Scrypto for that matter. I watched an interview where Piers, Ridyard, and Matt Hines and Jeremy Epstein explained in great detail how Radix had started from the ground up with the sole goal of DeFi. It was an interview with Ivan on Tech. He's now Morales, kind of comes from strongly in the Ethereum ecosystem. But he did a great job of playing devil's advocate and asking really hard questions, which made for a wonderful interview and really what sold me. So, what really got me as a builder is, I like to make things. So when we got to the hard technical questions and Matt started answering, what was really different at the core foundational level of the Radix system. And really by the time he got to the end of this explanation, I was done with Ethereum. I can remember as he explained the approach of building Scrypto as an asset-oriented programming language and how they had structured assets to follow the behavior of physical assets in the real world. I realized, I was like, oh my God, the tech is finally here. Well, almost, which is even better. Because with Babylon right around the corner, this is literally the perfect time to get in. Sorry, guys, I know you've spent 8 years getting here, and hats off to you for that. I know what it's like. My solar light tower patents took 9 years to get anywhere too. But with that night, I started reading the Scrypto docs from cover to cover. I stayed up all night till I finally fell asleep in place, having read about 2/3 of the Scrypto documentation site. When I woke up, I continued. I started finding anything I could to learn more. I watched a few of the Scrypto developer events that were up on YouTube. I searched for a quick start video on how to get up and running, and I couldn't find one. So I just followed the docs and started recording a video to show how to get started. I haven't stopped since. I'm at the end of about a 1.5 year hiatus, so I need to get back to work here pretty soon. We've all got to make money, but all I can focus on is Scrypto because I get to finally build the financial system I've been dreaming of for decades. So the one thing I can say is guaranteed wherever I land, it will be in the Radix ecosystem because the time is now. If you're watching this video, you're in the right place. Awesome. Can't wait to work with you. See you in the ecosystem. And that's about it for me. I hope you enjoy your Scrypto learning journey and welcome. Thanks. Thanks for listening to me rant. Have a good day.
Hi, my name is Matthew Hines. I'm the Chief Product Officer at RDXWorks. I'm here to talk to you today about NFTs. And where I want to start is just talking about what are NFTs exactly. And then I'm going to get into a little bit more about the future NFTs and why we think they're so interesting and exciting. So let's start with the basics. First of all, what is an NFT? It's a non-fungible token. That's what NFT stands for. Now, that's kind of a complicated term that doesn't tell you a whole lot, but people seem to be really excited about them. So why is it the world seems to care so much about non-fungible tokens? Well, the reason why is this kind of stuff hits the news pretty regularly these days. An NFT sold for $69 million. NFTs have been selling for huge amounts of money. They've been issued by Nike and other companies. There's a lot of excitement around NFTs and a lot of money around NFTs. But to understand what that craziness is actually about, we kind of have to go back a little bit because it's really pretty difficult to understand unless you've been really in it since the beginning. Looking from the outside, you can understand how someone looks at NFTs and goes, this is insanity. There's nothing here, and yet there's all this money. So let's take a little step back and talk about the history of NFTs and how we got to where we are today. So the story begins with Bitcoin in 2009. And Bitcoin is really kind of a simple technology in the end. Now it's become, it's something that everyone's aware of right now, but in the end, it really is just this one thing. It is a network that supports this one application. And that network, you can kind of think of as a distributed database. Blockchain technology, which Bitcoin was the beginning of, is basically a way of a bunch of computers on the open internet to create a shared database that we can all trust, where there's no company that's sort of calling the shots on what goes into that database and what comes out of it. So imagine if you have that kind of database, and I'm not going to go into how all that works. If you have that, you can do stuff with that. And Bitcoin as the network isn't just a database, it's also this application running on top of the database that basically is Bitcoin, the token, the thing that you're actually thinking about when you think about buying a Bitcoin or trading Bitcoin. It's about what you're basically doing is interacting with this application running on this network. So it really just does that one thing, the Bitcoin network. You can run these rules that creates token sort of behavior. It enforces the fact that there's only so much Bitcoin at a given point in time. And if I have some Bitcoin, it means that someone else can't have that same Bitcoin. No one can just decide to create more Bitcoin or to destroy Bitcoin that exists. It basically starts acting like digital cash, which was the point of Bitcoin. Now, you can argue the value of that digital cash, and this is a whole other point, but just in terms of the technology, you have cash-like behavior. You have the fact that you have this thing that you can hold, you can trust that it's going to continue to exist, and you can transact it around between people. That's basically what Bitcoin is. So if we go from there, if we fast forward a few years to 2015, we get to Ethereum. And maybe less of you have heard of Ethereum, I'm sure some of you have, but Ethereum introduced the concept of smart contracts to blockchain. Basically what that did is it made it much more flexible. The bottom part of it, the network part of it, the distributed ledger part is actually quite similar to Bitcoin, but it added more functionality to that application layer. Now, rather than just running this one simple application that just manages the supply of Bitcoins, now you had the ability of anybody coming to the network and deploying what are called smart contracts. And a smart contract is basically just a piece of code that runs on that network. The network runs it for you. It's kind of like a big mainframe now. Now, rather than just having this network that runs Bitcoin, now it's this open computing platform where anybody can deploy a piece of code and the network will run that piece of code for you. And all those little pieces of code, smart contracts, can talk to each other. That's all a smart contract is. I think it's actually kind of a weird term, smart contract, because it suggests something that I don't think it really is. It's really just a program running on a distributed network. So that's what Ethereum is about. And that was a revolutionary change. Now you had much more flexibility. Now you can imagine running all sorts of applications in this sort of open environment, and people started exploring interesting ideas. So, all right. We're trying to get back to NFTs, right? So let's get back to tokens. How do tokens fit into this big picture? Well, a token, a simple token, a token along the lines of Bitcoin or other tokens that you might have heard of, cryptocurrencies would be another way of looking at it. Tokens would be built in this kind of way in that environment. You would have these smart contracts, and each token is represented by its own smart contract. So maybe you've got a token called USDC, or you've got one called SHIB or WBTC or whatever it is. And each one of those smart contracts maintains its own little internal list. You'd have a list of, you'd say, I am represented by a particular address on that network, and I can have entries of that address in multiple of these token smart contracts. So let's say in the USDC smart contract, my entry has a 50 associated with it for my balance. What that means is I own 50 of the USDC token. And so that smart contract would have to implement logic that says, well, if I want to send tokens to someone, it needs to reduce my balance and increase the balance of somebody else. So you get sort of token-like behavior. So you can create tokens on Ethereum, and you can do whatever you like with them. You can build logic around this kind of stuff. And you, again, rather than just having a single Ethereum token, you now have all of these tokens that anybody can create. It's pretty simple, but that alone, a couple of years later, led to what was called the ICO craze. So ICOs were called initial coin offerings. Basically, once people realized that, wow, anybody can create a token and put it on with these decentralized network, people started thinking of things of what those coins could represent, and they started selling them to people. They said, well, I'm going to create a supply of these tokens. They represent something, and you can buy some of those tokens for me in this initial offering of that coin. And so you got a lot of more headlines that came out around 2017 that said, a startup just raised $4 billion without a live product. They basically put a coin out there. They made promises about what that coin was going to represent once the system was finished, and people raised a huge amount of money. So this also was a little bit crazy. This was sort of the NFT craze of a few years ago. Okay. This is all still talking about tokens, though, so we still need to come back to non-fungible tokens here. These are not non-fungible tokens. These are just plain old tokens. So what's a non-fungible token? Well, let's put it in the same terms. How would you implement that in this smart contract model? Well, as it turns out, it's really similar to regular tokens. Basically, you have this same structure. Every supply of a non-fungible token, an NFT, is also this list of entries associated with a number of addresses that users control. So now in this case, my address might be in this list, but rather than having a balance on here, it would have an NFT ID or something similar to that. It might be like, well, here are the Bored Apes smart contract that represents that particular set of NFTs. And this particular Bored Ape is represented by ID 34952, and that's associated with my address. Therefore, I own that NFT. And if I want to send that NFT to somebody, then I would tell the contract, hey, please assign a different address to NFT ID 34952. That's basically how NFTs work. Now, you can assign all sorts of other things to this as well. You don't just have to have the ID. You could put in more information associated with those NFTs. Maybe that information associated with the NFT can change over time, and it can change its meaning. But you have this idea of, I can create this ownership sort of behavior where it feels like, oh, I own this digital thing and I can control who owns it after me. So this is interesting. It's pretty simple in the end, but once again, that was enough to create the NFT craze of 2021. And we're back to these headlines again. That's basically all these things are. The NFTs that you see in the headlines are really just talking about a specific type of NFT where each one of those entries also points to a particular piece of art. And that piece of art might be a Bored Ape that you could use as your Twitter avatar, or it might be something else. It might represent, Nike has been doing some stuff as well, where you can sort of say, hey, I have a digital representation of a pair of sneakers that I own, and it has its own NFT ID. And so I have a digital sense of ownership of that thing. So it's kind of like having a certificate that's created by the artist or the creator of a thing that says the bearer of this certificate owns this piece of art. It's this certificate. And of course you can transfer that certificate. If you give it to somebody else, then they have the piece of paper that says, well, the original creator of this thing said, whoever holds this piece of paper owns this piece of art. And so now we can have this digital representation of something that now becomes transferable on these open ledgers that people can use. So as a result of this fairly simple thing, we've got lots and lots of these multi-million-dollar NFT projects, and also a lot of NFT platforms that can support this stuff. So we already talked about Ethereum that can do this, obviously, but they weren't the only one. They were just the first. We also have networks like Solana and Binance Smart Chain, and there are even these things called L2s like Polygon, which is that last one. Basically, an L2 is saying, well, we're not going to actually build our own network. We're going to build something as an extra layer on top of an existing network, and maybe it runs a little bit faster, has some special features. So there are all these people that are building platforms that are able for you to run these NFT smart contracts, and then those smart contracts become new things that people can own on the internet. That's basically what NFTs are. But where do we go from here? It's like, the example I've given is, Bored Apes and CryptoPunks and all this kind of stuff. Where does this go from here? Is this just a fad that we've put behind us, or is there something more to it? Well, it's definitely not a fad. Both for tokens and NFTs, there's quite a bit more here. We're just seeing the very beginnings of it. So now let's talk about the future NFTs and, in fact, tokens. Why are tokens and NFTs so important? Well, to predict the future of tokens, we need to understand why they're important. And the reason why they're important is that they can represent lots of different kinds of things. So a regular token, which would be normally called a fungible token, they usually just don't say it. They don't say fungible token, they just say token, is a thing that can represent value or ownership of some kind, and you can hold and trade with others. Again, kind of like we talked about before, but it can represent just about anything. What makes it fungible is the fact that it's totally interchangeable with any other of those tokens, kind of like a pile of nickels. I don't care which nickels I have. I just care the fact that I have 14 nickels that is worth something to me. I can exchange those nickels for a candy bar, something like that. They have some value that's associated with those nickels. And the source of that value can be a million different things. And you can have all sorts of arguments about what is money and why is it worth what it's worth. But basically, a fungible token is just sort of like, I've got a bunch of this stuff, and all of these tokens are all interchangeable with each other, and they're all worth the same thing, basically. Okay. A non-fungible token is a little bit different. As we talked about before, the way we would implement this on Ethereum is by having these entries in our ledger for individual serial numbers or individual IDs. Basically, if we generalize that, we can say that a non-fungible token is just a unique thing that represents value or ownership of some kind. So rather than being totally interchangeable, now each NFT represents something in a very particular way. You can't just swap between them freely. So it's more like, tickets to a basketball game. I might have tickets to seat B2. That's not at all the same thing as the ticket to seat C14. Those things are in different parts of the stadium. They have different value. They have different prices. I might choose to trade them with someone, but you can't say they're interchangeable. They have different meanings, even though there's still a supply of tickets to this particular basketball game. So this is, again, kind of like the Bored Apes. We have a supply of Bored Apes, but each one of those things has different values to different people because they like one ape more than another. And so you can have these unique representations. You can have each one of these things pointing to a piece of art, or really kind of whenever you want. So actually, let's talk about that whatever you want and generalize a little bit, because this is where we get into the real importance of these things. Let's dig a little bit deeper. So some other examples of what you can do here. So for fungible tokens, we can have crypto tokens. We've already talked about that. Don't need to go into it. We can also have something like USD tokens. There are actually today billions of dollars in USD tokens on these open networks, on Ethereum and other networks. And basically what these USD tokens are is they are backed one-to-one by actual dollars in a bank account. There's an issuer of the USD token, and they say, well, right now I've got $1 billion in this bank account, and therefore I'm going to issue 1 billion of these USD tokens onto Ethereum or one of these other networks. And so they say, I'm willing to swap those one-to-one. If you have one of these tokens and you give it to me, I'll give you an actual dollar in exchange in concept. And so the idea here is that now I have this tokenized representation of dollars, and I can exchange those things on the Ethereum network or other networks in a much more frictionless way. It's easier for me to do things with that tokenized dollar than it would be necessarily with an actual cash dollar or having to deal with a bank that was holding some dollars in a bank account. It becomes this very sort of, low friction, easy thing to deal with. I can start programmatically dealing with those tokens, and I'll get to that a little bit later. Other examples, a little bit less serious. It could represent money in a gaming world. It doesn't have to be all sort of real serious financial stuff. It could be that rather than having, my gold or gems or something like that in a gaming world where I only see it in the game, I could represent it as a token on one of these open ledgers and have that same sort of feeling of real ownership. We could also have tokens represent percentages of shares of a piece of real estate. So maybe there's a piece of real estate and I own 34.6% of that. Well, that might be represented by 36.4% of a particular supply of token that is associated with a piece of real estate. Once again, this is now something that becomes very easily transactable and very powerful. Or it could represent voting shares in a DAO. This is a whole other thing. DAOs are decentralized autonomous organizations. Basically, you can kind of think of it as a club or an organization where there are a bunch of members of that club and they have certain powers. They can vote on things and whatever. So it might be that I have some tokens and that represents how much power I have to vote in that DAO. So lots of different things you can do with tokens. Getting back to NFTs, we have a similar kind of list of things, but different sort of unique applications. So rather than crypto tokens, we might have collectible avatars. Again, this is something that we're very familiar with already. Moving into the financial world, you might have something like lending positions. So this might be that if I want to give someone a loan for some money, I need to represent that loan itself. I need to say, okay, it's kind of an IOU. You issue this NFT that says, this represents a loan for so much money, and in order to repay this loan, you have to pay this back with some amount of interest associated with it. And that lending position itself then becomes transactable. Maybe I sell that debt position to somebody else. This starts getting into all the wonderful abstractions of the financial world. It could also, once we get into gaming, it also could represent unique equipment in a gaming world. It might represent your sword or a particular piece of armor that you won that's been through a certain history in the game, and so it's unique from all other pieces of armor in that game. You could represent that as an NFT and make it transactable inside the game or even outside the game. You could represent a deed to a piece of real estate. So rather than a percentage of share, it might be that, well, my house is represented by this single NFT, and if I sell that NFT to someone else, that means that I have transferred legal ownership of the house to them. Kind of acts like a contract. It could also represent administrator access to a DAO. So rather than voting shares, it might be that there's someone that has like special singular powers in that DAO, and the NFT, it can kind of act like an access badge. They can kind of flash their NFT and kind of like, all right, I'm the admin here. I'm allowed to come in here and do very particular things in the system. These are all notionally really powerful things that you can do with tokens. You can see, and NFTs, you can see how flexible this is. And it creates a new concept. It creates this idea of truly digital personal ownership. It's the idea that owning something, you can own something in just the way that having something in your hand is owned by you, but doing it on an open ledger, doing it in an environment where you can do things much more programmatically. Now, that sounds very abstract, and you might ask, well, why do I care about that? Why do I need to be transacting things on an open ledger? Well, to explain that, I need to take you on a very quick tour of finance to understand why this is so valuable. Traditional finance kind of looks like this. This is a very simplified view, but basically finance, the idea of finance goes back to, roughly speaking, the Renaissance, when we had the rise of banks. And the reason why we had banks that came to be was to be able to do things that just simply cash couldn't do. If I just had a bunch of gold coins, it really limits what I can do with that money. Banks arose to be able to offer different kinds of financial products to people. They say, I want to be able to take out loans with some interest. I want to be able to invest in enterprises. I need to be able to have currency exchange between different types of currency. These are all very difficult things to do on any sort of scale with cash. And so banks came along and said, well, okay, if you're willing to trust your money to the bank, we will then have relationships between our banks. And because we can do that, we can do things that you wouldn't be able to as individuals. We can sort of collect money together, and we can offer lending and settlement and all these sorts of great financial things. That's the basic concept of finance that's been in place since the Renaissance all the way to today. And that same pattern gets used even outside finance. This is basically the model for, Web 2 as we think about it. It's sort of like applications we have on the internet. It's the idea that there are these institutions that are sort of managing the system on behalf of their users. So for example, if you've got an online game that you play, you might think of the fact that you own your equipment in the game, but really you only own it when you're logged into the game. You can't take it out of the game with you. You don't have independent ownership of that thing. So there is this sort of institutional model. So we had to do that with finance. We had to do it lots of other things because really that was the only way of providing a lot of these different solutions. But it can cause problems. You can imagine the finance space, if we're trusting all of our money to these banking institutions, well, what happens if there's a bank run? If suddenly everyone wants to get their money out of the bank at the same time? If there's not enough actual dollars in an account, you can create a panic. This is a big deal. It can cause things like the 2008 real estate crash, where it was hard to even tell where all these different real estate investments actually were. They become so abstracted through banks that there was really no transparency in what things were being invested in, what pieces of real estate. These are all problems that happen when we abstract these things into these institutions. But even those problems, it also just defines how the whole system works. Everything is reliant on these institutions, and it limits what you can do. So there's an important new concept, which is something you may have heard of, you may not, which is DeFi, or decentralized finance. It's very, very closely related to the concept of Web3 that people have also been talking about recently. The idea of DeFi and Web3 is to remake how these kinds of systems work in a different pattern. The idea here is that rather than trusting institutions to do these things on our behalf, we have more direct control of things. So if we take the finance example, it means that every individual in the system isn't transferring their funds to the bank and then doing things with the bank. They maintain access to their own assets. Now, Again, this might start making you think of tokens and NFTs that we talked about, because that's exactly the point. The idea here is we need to do this sort of thing on an open, neutral network. I need to own my assets on a network where I know there's no one that's going to take that control away from me. This is the same pattern that the internet itself took. It was the idea that we could move for communication systems that in the 80s relied on these big companies to make international communication possible. We moved to an internet model where now anybody could build applications on the internet and anybody could connect to the internet on exactly the same basis. We need to do the same thing with ownership, with finance, and with all these other kinds of systems. It's really powerful when you can do that, because it means that now applications can run on these open neutral networks and they can interact with these assets and these identities that we have on digital networks. And so as you imagine, if you think about how revolutionary the internet was for communication, we can get the same sort of things for finance and all these other new kinds of applications. We can remake these kinds of systems in a way where they're much more competitive, they're much more convenient to use, they're much more inclusive, and they're cheaper. And ultimately, they should be just as safe as systems based on centralized institutions. So when people talk about decentralization, this is the thing that they're excited about. It's the fact that we don't need to rely on these companies. We can build a system that's actually just much better this way. It's much more democratic, it's much more open, it's more transparent, it's more efficient. So what does this actually mean in practice? If we have this sort of DeFi system, let's look at a real example about how you would build something on a network like this. And this will bring us back to NFTs. So we can use these, if we can build networks that revolve around the notion of personal digital ownership, we can start to build things that we expect from the real world, but in a more decentralized DeFi sort of way. So let's take the example of a currency exchange, something we're all very familiar with. I can go up to a kiosk, I can give them some US dollars, and I can get some pesos back or something like that. If we want to rebuild this in the other model, basically what we want to do is write some code that can do the same sort of thing. So in the traditional world, a currency exchange is offered by a bank. They have these big reserves of different types of currencies behind the kiosk. I've got a bunch of dollars, I've got a bunch of pesos and euros and pounds and so forth. And so when someone walks up to the window, I can check a current exchange rate. I can put their money into one pot. I can take some money out of the other pot and give it back to them at the right rate. So how do we replicate that on one of these networks? Well, we might do it something like this. We might imagine a piece of code that can accept some tokens from an account and can do a little bit of calculation, can put those tokens into one, a vault of tokens or a pool of tokens, take some other tokens out of a different pool and send those tokens back to the user. And as long as I can write a piece of code to do that, cool, I've now replicated a currency exchange with what should be a really piece of code. You'd expect that this would be really dead easy to build, right? But remember that using the smart contract model we talked about earlier, we have to build everything within that pattern. So this really simple concept that we have for an exchange has to be expressed in terms of something that fits into this Ethereum virtual machine model, where I have a bunch of smart contracts running on that network and they can all talk to each other. That's the tool that I have to use. And so I have to use that tool to build that kind of system. And the big problem with DeFi today is that doing that makes the solution actually look more like this. It's really, really complicated. It's stupidly complicated. Something that should be this simple actually means that you have to implement each one of those tokens as an independent smart contract, and then your logic has to talk to those things. It has to check balances. It has to request these balance changes. It has to maintain its own internal cache of balances. It becomes this very complicated, messy thing. And what that means is that the more complexity is, the more work for the developer, the more opportunities for making mistakes, and the more opportunities there were for hackers to exploit this system, to find gaps in that logic to be able to pull tokens out where they weren't supposed to be able to pull tokens out. It's also a way, this example here, by the way, you'll see Uniswap on the slide. Uniswap is the biggest exchange on Ethereum today. And that's why it took the creator of Uniswap something like 1.5 years to get from their idea to a production-ready deployment of something that really should have been very simple. It's also the reason why there's literally a website called Rekt that does nothing but catalog hacks and exploits in DeFi today. So DeFi is running on Ethereum and people are doing lots of these financial things here. But literally, like every week, there are hundreds of millions of dollars that get stolen because of hacks and exploits. That is insane. That shouldn't be the case. And so what this means is that even though there's this enormous amount of potential in DeFi, it's really limited. This is why it hasn't taken off. This is why most people haven't even heard of DeFi yet, because you can look at the potential here. The global financial system today is something like $400 trillion. So this blue block represents that box. And that's why if we compare DeFi as it is right now, I just checked this as of October, it's about 0.05 trillion. So it's a tiny, tiny fraction. Its square doesn't even compare. It's less than a pixel on this chart. That's why the problem is, the reason why it's so tiny is because all of this promise that we expected from DeFi, we want it to be competitive and convenient, inclusive, cheap, and safe. It actually isn't. The potential is there, but the implementation of it, the way you have to build and the way you have to interact with these networks is really problematic. So this is why the only NFTs that we see really take off today are things that are really dumb simple, things that are so simple that they don't immediately break right after they're deployed. And basically what that means is Bored Apes and ICO tokens. There's nothing to them. They don't have very much logic. They do really one thing only. And so people found a way to use those things to do something that had a lot of value to people. But it's not where it ends. And so solving this problem, making DeFi really fulfill its promise, is why Radix exists. This is why we're here, and this is why we're talking to you right now. So I want to talk for a moment about what Radix is. Radix is the only decentralized network created to give builders everything they need to obsolete traditional finance. That's the mission statement. Basically what this means is what we're trying to shoot for is not just sort of build something that in concept is capable of doing these DeFi things. We're trying to build all the technologies that are necessary that allows developers to really take full advantage of the advantages that it should have. You should be able to build applications on this network that have all the same features that financial systems have, or any system that interacts with things of value and identity and all those sorts of things. You should be able to build on these networks, and you should be able to outcompete how the traditional way works because it's so much better. But we need to provide the right tools for that. So over the last 9 years or so, Radix has put an enormous amount of work into building a technology stack that can do that. And there are kind of two major parts to that technology stack. The first part is that we've really focused on building the Radix platform for builders. That means Scrypto and the Radix engine. These are our terms for these technologies. And what I'm going to talk about is as asset-oriented smart contracts. Scrypto is the smart contract language of the Radix network, and Radix engine is our own version of the virtual machine. It's our alternative to the Ethereum virtual machine. Those things are designed specifically to give developers the fastest possible path from idea to production DeFi dApp. A dApp, by the way, is a decentralized app, if that wasn't obvious. The other part of our technology stack is that we've focused on building it for scale, because if you imagine people start building thousands of these really powerful applications that start interacting with tokens and NFTs and doing amazing things, well, that network needs to be able to handle an enormous amount of capacity. It needs to keep up with the world's needs for transacting things. And so our solution to that is something that we call Cerberus. It is a braided cross-shard consensus mechanism. I won't get into what all that means, but basically the result of this is that the Radix network should be able to deliver unlimited dApp throughput, low fees, forever. This is the most important thing. Now, we're on a multi-year roadmap to deliver all this stuff, but we have a design for Cerberus that provides this capability so that as people start building stuff on our network, scale is never going to be an issue. We'll be able to implement Cerberus, and we'll be able to scale the network so that anybody can continue to use it without anybody interfering with anybody else. That's the point. So I want to focus a little bit specifically on the Scrypto and Radix engine part, because that's really relevant to what we want to talk about in terms of the developer experience. So to describe what the Radix engine is, remember, let's go back to the Ethereum way of doing things. This is how the Ethereum virtual machine works. You have a bunch of these smart contracts. They're running an environment. They can pass messages between each other. Cool. The Radix engine adds something crucial to the mix here. It adds what we call resources. And resources implement the concept of assets itself. Assets are now built into the platform. Rather than implementing a token or NFT as its own smart contract, now the platform understands what an asset actually is, which makes sense because the entire purpose of these platforms is to interact with assets of various types of tokens, all the different tokens you can imagine, all the different NFTs you can imagine, all these different asset classes. This is why the network exists. And so why should the network speak in terms of those assets rather than forcing people to re-implement those concepts in every single token and NFT? Having that totally changes the whole approach to how you build smart contracts in Radix. So for example, to make it concrete, as I said, tokens in your account looks very different on these two types of networks. On Ethereum and basically every other smart contract network today, as we saw before, you have a bunch of addresses that have a bunch of entries in these individual token smart contracts. On Radix, tokens are resources that are real things, if you want to think about it that way. Basically, the platform understands the idea of an account. An account is a container that can have these other things called vaults inside it. And those vaults can contain tokens. And those tokens have a certain quantity, and they automatically have certain rules associated with how you can transfer those assets from place to place. They're still very flexible, they're still very programmable, but the core notion of an asset is built into the platform. So you can imagine that the programming experience around interacting with tokens and interacting with accounts and everything else becomes very different. We call it asset-oriented programming. And Scrypto is the programming language we've created to run on the Radix engine to expose all this asset-oriented functionality to developers. What it means in the end is that the Scrypto implementation of Uniswap, that really simple swapping system we talked about, this was the concept that we had in mind. As it turns out, the Scrypto implementation actually really looks like this, and we can show you the code for this. It's basically, you can program a piece of code, and the method input, the method for that trade functionality on that smart contract actually accepts real resources. We didn't have to talk to a token smart contract. The platform understands the idea of taking a resource out of my account and transferring it to that smart contract, along with maybe some request instructions. And then my code can actually speak in terms of putting those tokens into one pool, taking tokens out of a different pool, and then pushing those tokens back to the user that called me. Those are all actual real calls. That's what the real syntax of Scrypto actually looks like. And that is incredibly powerful. And basically, that's NFTs and DeFi on Radix. It means that NFTs can move beyond being these super simple concepts that are a little bit weird and a little bit hard to understand why they're so valuable, and start moving into the world of things that are really valuable for 1,000 different applications. We think that's incredibly powerful, and it's going to revolutionize the way most things in the world work over the coming years. So for developers, we want to invite you into that. We want you to be part of that solution, making use of Radix and building that better world. So thanks very much for listening.
Hi, I'm Jeremy Epstein, the Chief Marketing Officer at RDX Works, the core developer of the Radix protocol. First of all, I really want to thank you for spending your time with us today. We certainly don't take it lightly that out of all the things you could have been doing today, you chose to spend the time with us. So thank you for that. Hopefully by now, you have seen and felt the power of what an asset-oriented development environment can do. You maybe even have visions of the opportunities awaiting you in the $400 trillion market for DeFi. And possibly you feel energized to join us on our mission to create a radically better financial system. So what do we mean when we say radically better financial system? Well, good news for you. On December 8th at RadFi 2022, you will have the opportunity to find out. That's where and when we will share our unique vision with the world, and we are going to unveil key components that are going to help you improve your time to market of potentially game-changing and secure DeFi dApps. So again, RadFi 2022 on December 8th. It's kind of like an event that you want to be able to tell your grandchildren that you were at. Okay, maybe not, but it's really going to be awesome. We hope you'll be there. RadFi 2022, December 8th. See you there.
got a very important phone call to make.
Get a minute, don't know. Get a minute of your time. Get a minute of your. I show that I live right, and I'm never gonna let you out of my side. I've been knocked out, was a nice try, but I guess I get to keep my head on this time. Part of the creation, the relations I've got, the only one that keeps me safe, the only one you should trust. For sure, it ain't right that I have checked the speck of dust from all of its side. Fall down, that from my height, cause I didn't see the plank I have in my eye. See the plank I have in my eye. You in yourself when no one's to be found. What keeps you is that what takes you off your mind. Yeah, you better. Cause you want this, I want this. Everybody in this, we should have it. Stop illusions, it's in your hands. Show yourself, reveal it to them. Yeah, you better. Take the time to recognize it. You won't leave me even if I tried it. You're the artist, I'm the mess, and happily perform the new in your hands. Yeah, you better. Yeah, you better. Cause you want this, I want this. Everybody in this, what should have it. Stop illusions, it's in your hands. Show yourself, reveal it to them. Yeah, you better. Take the time to recognize it. You won't leave me even if I tried it. You're the artist, I'm the mess, and happily perform the new in your hands.
the top three things that I enjoy about Scrypto is, number one, the analogy to real life. It makes so much sense the way Scrypto is doing things, with the buckets, with the vaults. I love the real, vault. I know, bank vault. I vault. I get it. Resources in motion go in buckets. At rest, they're stored in vaults. Is that I love that, right? And then the second thing is the proof. And then you guys use the word proofs. I love that. The proof is in the pudding. When I'm getting on Scrypto, it's matching. The logic is like, oh, they say it's like this, and it is like this. There's some people that say, oh yeah, we do this. You open up the SDK, you can't even get it to compile on other languages. You can't even, right? But it says this. And then I said, oh, where are the docs? I said, oh, the docs. And I looked at the docs, and they have all the methods to everything, and it's laid out clean on the docs. And I'm like, yeah, it's all there. So that's what I like about it. The proof is in the pudding. It really is doing the mission, and it is really smarter to do it this way and more secure. And then when you empty something out of a bucket, if someone tries to go into that bucket, there's nothing there, everything crashes, because that's how it should be. And I love, and the third thing is, I love that there's a major difference of of having a person be an NFT. I feel like it's not a big deal having a wallet and having it's more of, it's a different approach. And I feel like it's just more safe and secure this way. And it's using the non-fungible the way it was probably meant to be used by code. It wasn't meant to be a goddamn 8-bit dude with a fucking mohawk. It's not what the non-fungible token was meant to be. People think, oh, NFT, I do art as well. It's not art. NFT is not art. It's a data structure that's non-mutable. Let's say what it is. And I love that Scrypto is like, yes, a person can be an NFT because they are unique. You can't mutate Redfoo. There's no 50 Redfoos. There's one Redfoo, baby. I'm non-fungible. Fungible people out here. I'm not a copy. I'm not a clone. I'm not a Bitcoin. There's not 2 million supply of me. I am an NFT. And that's and on the Radix network, that's what I am. And I have a unique resource address to me. That's it.
Hello everybody, my name is Omar and I'm a developer at RDX Works. Today I'm going to be giving you an introduction on how you can build smart contracts on Radix using Scrypto. So I would like to first begin by providing you with an overview of what exactly we'll be talking about during this presentation. I will first begin by explaining to you what blueprints and components are. They are essentially Radix's form of smart contracts. We'll then talk about resources, which is Radix's implementation of tokens and assets through a finite state machine. We'll then, relating to resources, we'll talk about authentication and authorization in Scrypto. And then switching gears a little bit, we'll talk about accounts and transaction manifests. And then we'll end this presentation by doing a live coding session. During this live coding session, we'll build an escrow blueprint, essentially a blueprint where two parties can exchange assets. Party A can put some assets, party B puts some assets, and then these assets are exchanged in a trustless way between the two parties. There will be a Q&A session, but we'll do this Q&A session at the end of this presentation. When we get to the end, I'll show you a QR code, and you can scan this QR code. It takes you to a platform called Slido. And on that platform, you'll be able to ask any questions that you have, and I'll answer them at the end of the presentation. Let me tell you a little bit about who would benefit from this presentation. There are two main groups who I think would find this presentation to be useful, or who would benefit greatly from this presentation. The first group is developers who have already programmed on other blockchains in the past, or who have programmed on other DLTs in the past, and who hope to expand their knowledge and dive deeper into Scrypto. And so if you're somebody who has programmed in, let's say, Scrypto, Solidity, Solana, Plutus, or any other smart contract framework in the past, I think that you will find this presentation to be helpful, as it will give you a good introduction into Scrypto. I think that if you're somebody who is a general developer, I think that you will still find this presentation to be useful. Now, I want to talk a little bit about some of the assumptions that I have going into this. The first assumption that I have is that you've already installed the Rust and Scrypto toolchains. If you haven't done that already, then scan this QR code. It takes you to a web page that has all of the instructions on how you can go about installing Scrypto on your local machine. I'm mainly making this assumption for two main reasons. The first reason is because of the live coding session that we'll be doing at the end of this presentation. Some of you might choose to follow along and code along as I build this escrow blueprint, so you will need to have Rust and Scrypto already installed to be able to code with me if you want to do that. Some of you might not want to do that, and that's fine. In addition to that, we'll be having a challenge at the end of this presentation or after this presentation. And to be able to do that challenge, you'll need to have Rust and Scrypto installed. And so you'll need to have these things installed. Again, if you do not have them installed, just scan this QR code. It takes you to a web page with the instructions on how to do that. I'm also assuming that you have some programming experience. And I'm not too particular about which programming language you've used in the past. Could be Python, could be C, could be C++, it could be whatever programming language in the world. I'm just operating with the assumption that you understand what a function is, that you understand what a variable is, that you understand all of these different concepts about programming, and that you already have a good idea about programming. Of course, Rust knowledge is preferred, mainly because crypto is based on Rust. So some Rust knowledge is preferred, but not required. So with all of that out of the way, let's begin with the presentation. And the very first thing I would like to talk about is blueprints and components and what exactly they are. And I will begin by telling you what a component is. If you're somebody who comes from the Ethereum world, you can think of components exactly as smart contracts. Components hold state, components hold data. You have methods that you can call, and by all means, you can think of components as smart contracts. But one thing that components don't have is that they don't exactly have any logic in them themselves. All of the logic that components follow is stored in blueprints. So if you're somebody who comes from an object-oriented background, I think that the relationship between blueprints and components is going to be immediately clear to you. You can think of a blueprint almost like a class or a struct, and you can think of a component as being an object of that class or struct. And so the blueprint is meant to define the structure that components will have. It's meant to say this component is going to have this type of data and this amount of data. These are the methods and functions that the component will have, and this is the logic that is tied to these methods and functions. And then if you have multiple blueprints together, you combine that into something that we call a package. And one of the questions that I typically get from people is, why exactly is the actual code in the blueprint and not in the component? Well, the main reason behind that is ledger bloat. You do not want your ledger to be bloated with copied data. And so let's say that you've got a popular blueprint and you've got many components instantiated from this blueprint. Well, all of these different components are going to be following the same logic. And it doesn't make a lot of sense from a storage point of view to just copy and paste this data and copy and paste this data again. What makes sense is, since all of these different components belonging to the same blueprint, since all of them are going to be following the same logic, it makes sense not to copy this, but to have it in one place, which is on the blueprint itself. Let me give you a bit of an example on how this relationship between blueprints and components might be useful to you when you begin programming in Scrypto. Let's say that you decided that you wanted to build a Uniswap clone. And the very first thing that you wanted to build is a liquidity pool implementation. And you said, okay, I'll begin by building a liquidity pool blueprint. On my liquidity pool, I'll define the types of tokens that I'll be storing. I'll define the types of data that I will have. And I'll also define the functions that I expect to find in a liquidity pool. Now, from this one individual blueprint that you've created, you can then come and instantiate multiple components. And so this one individual blueprint was useful for us because we used it to instantiate a BNB XRD liquidity pool component, ETH ADA liquidity pool component, and XRD BTC liquidity pool component. And we were able to do that without requiring an external factory that does all of these things for us. Instantiating components from blueprints is a system level feature understood by the platform itself. And there are many types of state that the blueprints or that components can have. And one of the things that you saw here is that we've got this idea of something called a vault. And to explain to you what vaults and buckets are, I first need to tell you a little bit more about resources. So what exactly are resources? Resources are Radix's implementation of assets and tokens, and they are implemented through a finite state machine. And so this implementation is actually native to the platform itself. And what that means is that the platform understands what a token means. It understands that tokens have certain characteristics that all of them share. It understands that a token can be created, can be minted, can be burned, that a token can have some kind of metadata. As an example, that a token could have a name, a symbol. It understands all of these different things natively. And so if you're somebody who comes from the Ethereum world, this is a completely different approach, because in Ethereum, if you want to create a new token, you define an ERC20 token or ERC721 or whatever standard you're using. You define a contract that adheres to that standard, and you say, I've created my token. And so you have to go out of your way to define an entire contract, and underneath the hood, your contract is actually defining all of the asset behavior and all of the behavior that the token is going to follow. And in the Ethereum world, you sort of have to do this because the EVM does not understand what tokens are. The only token that it knows is ETH, and it doesn't know about any other token. And so you have to do all of this in Ethereum, but you do not have to do this in Radix. Matter of fact, you can create tokens without needing smart contracts. You can create resources without needing smart contracts. And this is what we have on Olympia right now, resources without smart contracts. And again, all of this is possible because they're understood by the platform itself. They are a native feature of the platform. And whenever you want to create a new feature, and whenever you want to create a new resource, you go to the Radix engine, you say, hey, I would like to get a new resource, and that is created for you. And so resources in Radix are implemented through a finite state machine. They're not implemented through Turing complete smart contracts. They're implemented through a finite state machine. And we'll be talking about this finite state machine implementation and the benefits that it provides in a little bit. First, I want to talk about the types of resources that you can have in Radix. There are two main types of resources. There are fungible resources and non-fungible resources. These two mean exactly the same as you expect them. Fungible resources are interchangeable and identical. Non-fungible resources are individually unique and individually addressable. And so this is the main difference between them. And all resources have to always live in a resource container at all times. So a resource must always live in a resource container at all times. And that resource container may either be a bucket or a vault. And these two concepts, buckets and vaults, have a few things in common. Both of these are resource containers. And again, resources always need to live in resource containers. And both of these can only hold a single resource address at a time. So what exactly do I mean by they can only hold a single resource address at a time? I mean that you can have a bucket containing XRD and another bucket containing BTC, and another bucket containing ETH. However, you cannot have a bucket containing XRD, BTC, and ETH all at the same time. These have to be separated into 3 different buckets, since a resource container can only hold a single resource address at a time. So what exactly is the difference between buckets and vaults? Well, buckets are meant to be temporary and transient resource containers. They're meant to only exist for the period of the transaction. When the transaction finishes, buckets cease to exist. And if a bucket is found to exist after the end of a transaction, then that is a runtime error. And the Radix engine tells you there is a bucket that you sort of mishandled or did not correctly handle, and you have to sort of fix that issue. Vaults, on the other hand, are meant to be permanent resource containers. They're not transient, they're permanent, and they are stored inside of components, and they cannot be moved around. And so, essentially, the biggest difference is that buckets are temporary and transient, vaults are permanent and cannot be moved around. And so, if I wanted to sort of represent the relationship between buckets and vaults in a diagram, this is the diagram I would use. Say that we have 2 components, and each component has a vault. Sorry about that. Each of these 2 components has a vault. And let's say that the first component wishes to send some tokens to the second component. So what it does is that it takes the tokens out of the vault, takes them out of the permanent resource container, it puts them in a bucket, it puts them in a temporary resource container, and then it passes the temporary resource container to the component, and the component empties that bucket into the vault, and this is how the transfer happens. And so a bucket is usually used when you want to transfer tokens between 2 vaults. So now that we've talked about buckets and vaults, I can finally talk to you about the finite state machine that we use to implement resources, or the finite state machine on which resources are implemented. This is a high-level overview of what this finite state machine looks like. And so let's actually take a look at the, let's say, life cycle of a resource, and let's see how it maps to this finite state machine. So in the beginning, the resource does not exist. There is no possible state transitions that you can make. The resource simply does not exist. And the resource comes into existence by being minted. And so there was no resource, and then the resource was minted, and this state transition was performed, and the resource was put into a bucket. Again, buckets are temporary resource containers. Once we've created this resource and we have it in a bucket, perhaps we'd like to put it in a vault in our account, or perhaps we'd like to put it in a vault in a component that we control. And so we can perform this state transition from a bucket into a vault. And maybe after we've had this resource in our vault for some time, we wish to take it out into a bucket. Maybe we wish to send it to somebody else. So we take it out of that vault by performing a state transition and putting it in a bucket. And maybe once we have it in a bucket, we wish to send it to somebody else. We wish to give it to somebody else. And so we wish to put it in some other vault. And so we can then perform the state transition again. And maybe this other person is now doesn't need the resource anymore. So they can put it back in a bucket. And then if they want, they can burn this resource by performing this state transition right here. So if you look at this finite state machine implementation of resources, I think that one of the questions that you might have is, well, how exactly do I modify the resource behavior if I want to? Because in Ethereum, when I'm let's say writing my ERC20 token, I can write some logic to say that only this person is allowed to mint my token. Only this person is allowed to, let's say, burn my token. So with a finite state machine implementation, how do I go about doing that? Well, the way that you would go about doing it is by specifying the conditions required to perform a state transitions, or when exactly can a state transition be performed. And so the example I would like to give you is an example of a soul-bound token. How would we go about implementing a soul-bound token? And I want to talk about soul-bound tokens for one main reason, mainly because it shows in a really good way how you can modify your resource behavior so that you can do interesting things with your resource. And so if you do not know what a soulbound token is, a soulbound token is a token that once minted and given to an account, it cannot be taken out of that account, cannot be sent to somebody else, and cannot be burned. So how exactly do I go about making a soulbound token using Radix's finite state machine? Well, we said that we want to limit who can mint the soulbound token. Obviously, we don't want anybody to be able to create our soulbound tokens. They're our at the end of the day. So we can limit who can mint these tokens by limiting who can perform the state transition. So in this example here, I wanted to have some complex authorization. So I wanted to say that only an admin and 5 shareholders can perform a mint state transitions. When an admin and 5 shareholders approve of this operation, then the minting can actually be performed. And so this is an example of that. And then once the resource is minted, anybody can deposit it into a vault. Once it is deposited into a vault, you can see that this part is grayed out. We cannot take it out of our vault. It is not allowed to perform the state transition, and we've coded it in a way so that the state transition is not allowed. Token can only be deposited into a vault, but may not be withdrawn from a vault. And so this is how you go about modifying your resource behavior. You essentially control who is allowed to perform the state transition, and by doing that, you control the resource behavior. So what exactly are the types of things that you can control on the resource behavior? What exactly are the types of things that you can modify and change? Well, you can control who, if any, is allowed to mint or burn the resource. You can control who, if any, is allowed to withdraw or deposit the resource. You can control who, if any, is allowed to update the metadata on the resource. And so if you do not know what metadata is essentially, let's say, the name of the resource, the symbol, the description, and all of these different things. It's the resource metadata. And so updatable metadata controls who, if any, is allowed to update the metadata of the resource. And the final thing, which is not yet implemented, is who, if any, is allowed to recall that resource. And being able to recall a resource is essentially being able to say, I have given you this resource, but I can take it away from you at some point of time if I want to. So why exactly did we sort of change the approach? Why did we go about implementing a finite state machine for resources and for tokens, and why didn't we just follow the same thing that Ethereum had? Well, there are many different reasons, but to simplify, the idea of a finite state machine, or implementing tokens and resources in a non-Turing complete way in a finite state machine, makes tokens and resources a lot more intuitive and easy to understand and easy to reason about. You sort of have an idea of the sort of allowed states that a resource can be in, and if you wanted, you can also query when are these state transitions possible and when exactly are they allowed. And so it makes resources very easy to reason about and very easy to understand. In addition to that, any states which have not been enumerated are impossible, and the biggest advantage, in my personal opinion, is that it provides you with a greater deal of guarantees and more transparency. And what I mean by that is, let's say we just talked about recallable resources. Recallable resources are resources which somebody can give me but can also take away from me at some point of time. The idea of higher guarantees and transparency is the idea of me knowing that a resource is recallable even before it's been given to me. Me being able to, let's say, go to some kind of an explorer and see, oh, this resource is recallable, and these are the conditions required to recall that resource. Or, as an example, this resource is not recallable at the current moment of time, but it can become recallable in the future. All of these different things and transparency guarantees are provided to you mainly because of the finite state machine implementation. You will not be able to do something like this with a Turing complete implementation, mainly because Turing complete implementations are essentially black boxes. You don't exactly know what is happening in that black box unless you're able to read code. And this is why finite state machines provide a greater deal of guarantees and transparency. So we've talked about components and blueprints, and we've talked about resources. I now want to show a little bit of code to show you how all of the stuff that we talked about maps into actual code. Now, this might be your very first time seeing Scrypto code, so let me actually walk you through what all of this is doing. The idea of this code is that we would like to create a resource or a new fungible token, and would like this new fungible token to represent company shares. We would like to be the only ones able to mint company shares, but would like anybody who owns company shares to be able to burn them if they do not want them. And would like to initially begin with 1,000 company shares. So this is how you represent this in code. And let me walk you through how the things that we've talked about map into this stuff. We talked about there being two types of resources, fungible resources and non-fungible resources. When you're first creating your resource through the resource builder, you can specify the type of resource that you want to have. And so in this case, we said that we want to create a new fungible resource. But we don't have to do that. We can also say, hey, I want to create a new non-fungible resource if we wish. In addition to that, if you recall the finite state machine when we talked about it, we said that when a resource is first minted or when a resource is first created, it goes into a bucket. Recall that a bucket is a temporary resource container. And so with this, when we first created this resource, it goes into a bucket. It goes into this temporary resource container. Also, this is how you actually restrict who can perform the state transitions in code. This is how you represent all of this in code. So in here, I said that my resource is mintable. My resource can be minted at a later point in the future. And I require that, and only admins are able to mint my resource. And I do not wish for the rule governing, I do not wish for the state transition rule to be changed at any point of time in the future. This rule governing this state transition is permanent and will not change. On here, I said that my resource can be burned, and I said that my resource can be burned by anybody. If you have the resource, you can burn it. And I ended this by saying I would like to create an initial supply of 1,000 of this resource. And so this is how all of the different theoretical concepts that we talked about during this presentation sort of map into actual code. And I wanted to only show resources here because we'll be talking a lot more about components and blueprints during the actual live coding session. So relating to all of this, I now want to expand a little bit more on the two lines that you see here, mintable, burnable, and I said rule require admin badge and rule allow all. I want to now switch gears, talk a little bit about authentication and authorization in Scrypto and how exactly that is done and how that is handled. So throughout this presentation, for simplicity, I will be referring to authentication and authorization as auth. So I'll just be using one word for it, and I'll be using the word auth to represent that. So what exactly is authentication and authorization? We must first know what exactly are we talking about to sort of know why is it important. Authentication and authorization can be described as the ability to verify a claimed identity based on that restrict or allow access to certain parts of our system. And why exactly are we talking about this topic that seems like it comes from the Web 2 world? Why does it seem like we're about to begin talking about JSON Web Tokens all of a sudden? Well, the idea of auth is very important in smart contracts or blueprints and components as we call them here. The idea of auth is very important because virtually every single smart contract out there might wish to limit or protect access to certain parts of it only to certain people. And so you might have some methods or functions on your component that are restricted only to admins. Only admins are able to call them. And so it's a very important topic, especially when we talk about smart contracts. And with Scrypto, we decided to follow a completely different approach to auth. The approach that you might be used to when it comes to auth is the address-based way of saying, this is the address of the admin, and any message that comes from this address will just assume that this person is authorized to perform this just because they have the correct address, and therefore they're likely to be the right person for this. And so authorization in most other blockchains is primarily based on the address of the caller. But with Scrypto, we have a bit of a different approach. Scrypto's auth is based on what you have and not who you are. And so in Scrypto, authorization or auth happens through badges. So what exactly are badges? Badges are just normal resources. And we do authorization by what you have and not who you are. And when I want to say that you have access to this part of the system, I say that I wish to restrict access so that only people with this badge are able to access this part of the system. I then mint a new badge and give it to you, and now you can do authorization based on what you have and not who you are. You've been given a badge to prove who you are, and now you can present this badge when you need to authorize you to access this part of the system. And this is actually very similar to how we usually do auth in the real world. When we want to do auth in the real world, we give some person a badge with, let's say, the security clearance that they have, and the badge that they have defines the security clearance that they have. And based on the badge that they have, it defines the parts of the system that they can access. So it's very similar in Scrypto. It's based on what you have and not who you are. And a very important point that I want to talk about is that your badge, or any badge that you have, does not need to be passed around. It only needs to be shown. And I want to explain this in a little bit more detail. What do I mean by a badge does not need to be passed around, it only needs to be shown? This relates to the idea of proofs in Scrypto. So what exactly is a proof? Let's walk through this example to understand what exactly a proof is, and then I'll go back to that point to fully explain what it means. Let's say that we have some individual here. This individual has 1,000,000 MyCoin, and he wishes to prove to somebody that he is in possession of 50,000 MyCoin, that he has got at least 50,000 MyCoin. He wishes to prove that he is in possession of that. And he wishes to do that on-chain. We're not talking about going to some kind of explorer or off-chain service to do that. He wishes to prove ownership on-chain. And he doesn't want to do this the primitive way. He doesn't want to send somebody the money and tell him, send it back to me. Now you know that I have it. He doesn't want to do all of this primitive stuff. So how exactly can this individual prove that he has 50,000 MyCoin on chain? Well, what he can do is that he can issue a proof of these 50,000 MyCoin. As you can see here, the person had 1,000,000 MyCoin, and after creating the proof, the person still has 1,000,000 MyCoin. The proof does not hold the tokens. It's a proof that he is in possession of the tokens. It's something that says this person is in possession of this amount of tokens. He does indeed have them, and here is proof of that. And I wanted to talk about this mainly because of this point. A badge does not need to be passed around, only needs to be shown. When you want to show parts of the system that you have a badge and that you're able and that you're actually authorized to do something, you create a proof of that badge. Your badge remains in your vault, and you only transfer a proof of that badge and not the badge itself. And so it always remains in your vault. It always remains in your possession, and you only send or show a proof of that badge. So this is what this point right here means. So let me scroll down. So why a different auth system? Why do we want to do auth based on what you have and not who you are? Well, this is largely because of the problems that exist with address-based auth. There are multiple problems that exist with it. The very first problem is that if you have not implemented auth handoffs, they essentially become impossible. So let's say that you've created an application and your application has become successful, and now all of a sudden you wish to sell that application to somebody else. Well, if you have not implemented a way to do auth handoff to say the admin is no longer this address, it is that address. If you haven't implemented that, well, you're kind of screwed. You'll have to sell your private keys to the person who wishes to buy the dApp. And that's not exactly a very user-friendly choice, not exactly the best choice to make. It's also very closely tied to your account and your private keys, and it assumes a one-to-one mapping of these two things, which isn't exactly the case in Scrypto. In addition to that, in the current implementation of address-based authorization, it is very, very difficult to represent complex auth. And what I mean by complex auth is something like this. Let's say that I have certain parts of my system that I wish to restrict access to, so that they can only be accessed if a supervisor, admin, and super admin approve of the operation, or a founder and 8 shareholders. I've got this part of my system and I wish to restrict access to it such that only when this rule is satisfied can this part of the system be accessed. Representing this at the current moment of time on Ethereum with address-based authorization is very, very difficult. But this exact same thing on Scrypto is very easy to represent, where you can just create a new access rule saying require a supervisor badge and an admin badge and a super admin badge. So it's this branch right here. Or, so this is where the or is, require a founder badge and 8 shareholder badges. A founder badge and 8 shareholder badges. And this is what this access rule looks like in Scrypto. You can then take this access rule, link it to some method that you have, or maybe say that only this access rule is allowed to mint my token, or whatever it is that you wish to do. But this is how you'd go about representing such complex auth in Scrypto using access rules. So switching gears a little bit, I want to talk about accounts and transactions. So far, we haven't talked about accounts at all. So what exactly is the deal with accounts? Well, accounts in Radix are just components instantiated from the account blueprint. As you can see, it's a normal component instantiated from the account blueprint. And one of the biggest advantages of accounts on Radix is that they natively support multi-signatures through the concept of access rules that is discussed in previous slides. And I'm mainly talking about this. You can do very, 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 very incredibly interesting auth rules on your account through access rules. And you can set up really crazy accounts, stuff like I can withdraw from my account, or my friend or this other friend can withdraw from the account. Or you can do interesting stuff like me and my sibling can withdraw, or any of my parents. You can do a lot of interesting stuff with this idea of access rules. And so it isn't just multi-signatures, it is complex authorization in general is very easy to do and very easy to implement with Radix's implementation of accounts, and it is very beautiful in my opinion. On the account blueprint, and so this third point is very specific to the implementation of the blueprint. Vaults are automatically created when a new token is deposited. And so in this image that I have right here, we've got 3 different vaults for USDC, SHIB, and wrapped Bitcoin. Let's say that somebody comes in and they want to deposit ETH into Alice's account. Well, there's no vault for that. No problem. As soon as that deposit comes, a new vault is going to be created for ETH, and ETH is now going to be stored in that vault. And so when a new token comes in that isn't recognized, a new vault will be created for that token so that it holds that token. Again, recall, vaults are permanent resource containers. So now let's talk about transaction manifests and what they are. And transaction manifests, it's one of the biggest features in Radix and in Scrypto, and it's probably a topic that I can spend an hour talking about, but I'll give you a high-level overview of what a transaction manifest is, what it does, and the kind of advantages that it gives you. A transaction manifest is meant to define the movement of assets that must occur in a transaction. It's also meant to define the limits and constraints to put on assets in the transaction. So what does that mean? I can build a transaction manifest that says, so when we talk about asset movements, I can build a manifest that says, swap some XRD for BTC, and then swap some BTC for LTC. This is what asset movements is like. So send those tokens to the decentralized exchange, call this method on this component, and so this describes the asset movement. I can then put some limits and constraints on my transaction. So I can say, swap my XRD to BTC, swap my BTC to LTC, that's asset movements. Make sure that after the swap, I get 200 LTC back. And if I do not get that, I'm not interested in the transaction. Just allow the transaction to panic and fail, and I'm not interested in the actual swap any longer. And so this is what I mean by saying you can actually put limits and constraints on the transaction and the outcome of the transaction. In addition to that, the transaction manifest describes or has instructions that must all execute atomically. And what I mean by must execute atomically is that all of the instructions must succeed. If one fails, then the whole transaction fails and nothing gets committed to the actual ledger state. And I put a little asterisk here to say that when I said none of the state changes are committed, this isn't exactly very true. Some state is committed, which is the fees. The fees get committed, and so the fees get taken away from you, but all of the other state changes that occurred in this failed transaction do not get committed to the ledger state. And I just wanted to define or talk about this a little bit. So transaction manifests, quick summary. They define the resource movements that must occur in the transaction. You can use the transaction manifest to put limits and constraints on the transaction. And it defines things that must all occur atomically in the transaction, meaning all instructions in the transaction must work. If one of them fails, then the whole transaction fails, and none of the state gets committed except for the fees. So with this, I've provided you with a high-level overview of the different concepts that we have in Scrypto. So let's now switch into the live coding session, and let's now begin talking about what exactly we're going to be building during this live coding session. So as I said during the beginning of this presentation, we will be building an escrow blueprint on Radix using Scrypto. So if you do not know what an escrow is some kind of service that allows people to exchange assets. As an example, let's say that I have some BTC and I wish to exchange my BTC for, let's say, ETH that somebody else has. And so I'm stuck in this thing where I tell him, you send me first and I promise I'm going to send them to you, which is very primitive. Well, escrows are meant to solve this problem. Escrows are essentially third parties. I send my assets to the escrow. The other party sends their assets to the escrow, and then the escrow performs the exchange. The escrow gives the other party's assets to me and gives my assets to the other party. And so this is what an escrow is meant to be about. So let me show you what all of this looks like in diagrams. We've got two users right here. These two users wish to exchange some tokens between one another. They wish to exchange some assets between one another. And they do not want to do it in the primitive way. So they involve an escrow component. You can think of an escrow component as being a very, very simple component. It's got two vaults, one for this party, one for that party. This party is going to deposit its funds into this vault. The other party is going to deposit its funds into the other vault, and then the exchange happens. So the first party takes the 10 BTC out of its account in a bucket and deposits it into the first vault in the escrow component. The second party does the same. They take their agreed amount of funds out of their account into a bucket and they put it into the second vault. Now that the two parties have deposited their funds into the escrow account, the exchange actually happens. So the funds that used to be here now go to this account, and the funds that used to be here go to that account, and the exchange of funds happen. The biggest advantage of doing this in DeFi is that the whole process is trustless. The escrow that I'm involving in this transaction or in this operation is some code. I do not have to trust a human third party to actually be honest and to do all of the escrow stuff for me. It's code, and I trust that if it has worked before, it will probably work now, and it will perform the whole transaction for me, or it will perform the exchange for me in a trustless manner. So let's talk a little bit more about some implementation specific details of what the implementation of this is going to look like in Scrypto. The way that I plan on doing this is that each party will be given an NFT, and the NFT is going to be used to authenticate and authorize the two parties. And so, as an example, if I am one of the parties involved in the escrow, I will be given an NFT saying Omar has to pay this amount and Omar should be given this amount. The other party is also going to be given an NFT, and the NFT is going to say this party has to pay this amount, and this party should expect to be given this amount of tokens. So it describes the sort of contract between the two parties. So this is what these 2 points mention. And this NFT is going to be used to authenticate users. And so once the exchanges actually happen, the user can take this NFT, go to the escrow component and say, hey, you owe me some money from this exchange. I would like to withdraw my money from you. And so it will be used to do this, authentication of users as well. So without further ado, let's get into actual code. I've prepared some boilerplate code for us. I mainly prepared this boilerplate code to make it easier for us to do the actual Scrypto code, so that we don't have to focus on all of the other boilerplate stuff. However, I will still go through the boilerplate code, explain to you what it does, and explain to you the different functionality in that code. You can find the boilerplate code in this QR code right here. Scan this QR code. It takes you to the boilerplate code. Once you're there, if you're familiar with Git, just do a Git clone of that code, or if you do not want, you can copy and paste the code if that is easier for you. So let me actually switch to my IDE here and let's begin coding. All right, so I have the code cloned. I have it opened up right here, and I've got my code editor ready for me to actually begin coding. So I am using the same boilerplate code from the QR code that I provided you. Now, in this code, I've included tons of documentation strings, and I've mainly included them to help you in the challenge that we're going to be having later on. And to be clear, the challenge that we'll be having later on is going to be based on this escrow blueprint. And so, yeah. So I mainly included all of these doc strings to help you in the challenge, so that you've got some resources to read, you've got some things to read, and you have a bit of a clearer idea about what each of the functions and methods are meant to be doing, and about the different things represented by the different structs. However, I also realized that doc strings can be sometimes a little annoying. So if you find them to be annoying, you can just collapse them from here on the side. So I'm going to collapse them, and I'm mainly doing that to make it easier for us to do the live coding. When needed, I will expand them and talk about some of the stuff that the methods will be doing. Okay, doc strings all collapsed. Yep. So I'm not going to begin with the blueprint. Matter of fact, I'm going to collapse the blueprint as well. I'm going to begin with the different enums and structs that I have already defined for us. Let me first begin with this resource specifier enum. I'm using this resource specifier for people to be able to specify the amount of resources that they're expecting. As an example, let's say that party A will be paying 500 fungible tokens to the other party. So they'll be using the fungible variant on the resource specifier enum. Let's say that the other party is going to be paying back 2 NFTs with a very specific ID. And so the resource specifier is used to specify resources that may either be fungible resources or non-fungible resources. The fungible variant has two data. The first data is the resource address. The second is the amount of tokens. The non-fungible variant has a resource address as well, but instead of an amount, it has a set of non-fungible IDs. And also, to be clear, every single non-fungible token has an ID. And so if you wanna specify a very specific non-fungible token, we specify that using the non-fungible ID and the resource address of the resource. So this is what the resource specifier does. Again, high-level overview, quick summary of what it does. It is used to specify some resource amount or some IDs of a non-fungible resource. But one of the things that we have to note about this resource specifier enum is that there is a possibility that it could be invalid. As an example, let's say that I want to say that the first party has to pay 500 XRD. Or let's say that I wish to say that the first party has to pay some amount of XRD. Well, the amount of XRD cannot be less than or equal to 0. It has to be more than 0. And so on the resource specifier, I have a method that I implemented which does some validation for me. One of the validations that it does is that it checks. It checks that if the amount is smaller than or equal to 0, then we've got an error. We've got something wrong in here. The validation fails. And so it validates that, that the resource specifier actually makes sense. And the non-fungible resource specifier could also not make sense. And it could not make sense in the case that we specify an empty set of non-fungible IDs. We say that this party is going to give me some tokens and I will give them no NFTs. It doesn't make a lot of sense. There has to be at least one NFT given. So when verifying or validating a non-fungible resource specifier, we say that if the non-fungible ID set is empty, then that is an error. Something is wrong here and something is incorrect. If it is not empty, then it's okay. Then, the validation passes and we're all good and we've got no problem at all. So again, when does the validation fail? The validation fails if the amount is less than or equal to 0 on a fungible resource specifier. It also fails if the set of non-fungible IDs is empty, and that sort of thing doesn't really make a lot of sense. So aside from the resource specifier enum that I've defined, I've also defined for us an escrow obligation struct. Remember during the presentation when I told you that every party is going to be given an NFT? Well, each NFT has some data, and this is the kind of data that our NFT is going to have. It will have the type of escrow obligation. The escrow obligation defines the amount that we will need to pay. It defines that as a resource specifier. Again, could be fungible, could be non-fungible. It also defines the amount of resources that we expect to get. Again, it uses the resource specifier for that. So we could get back some fungible or non-fungible resources, and this is the specified amount of resources that we'll be getting out of the exchange. And so again, what is the escrow obligation? I told you that every party is going to be given an NFT. The escrow obligation is the data that will be on that NFT. It defines the amount that this party should pay and defines the amount of tokens that this party should get back. So now that we have gotten the escrow obligation and resource specifier enums and structs out of the way, let me collapse those and let's get into the actual escrow blueprint. I've defined the struct and implementation of the escrow blueprint, but I've left a few methods out for us to actually implement them right now on the spot as we go and actually live code them. But I've defined for us one method right here. So let's actually go through everything that we have here and talk about what exactly we have. If you remember the diagram that I showed you, where I told you that an escrow is going to have two vaults, I wish to represent the two vaults as a map. Let me expand this here. So I wish to represent this as a map, as some key value store, where the key is a resource specifier and a vault is just a vault, is a permanent resource container. This resource specifier is of the amount that we expect to be paid to this vault, and the vault is the actual container. So the amount that we expect to be paid to the vault and the actual vault, and that is a key value store or a mapping. I did it in this way since it will provide us with some very nice abstractions when we're doing the coding, and it will provide us with some very clean code once we get into actual coding. And this is why I decided to represent the two vaults as a mapping that maps a resource specifier of the amount that the vault is meant to contain to an actual vault. Alternatively, you could say, I don't want to do it as a mapping. Maybe I want to do, let's say, two state variables, something like vault 1, which is a vault, and amount 1, which is a resource specifier. You could say that you want to do it this way, and this is certainly possible. However, this just comes down to preference of how you wish to structure your code, and you can certainly do it in this way. For me, I found this mapping of resource specifier to vault to be the easiest thing to work with. I also told you that each party is going to be given an NFT. In here, this is the resource address of the NFT that we'll be providing. So maybe I should tell you a little bit more about what we have here. This is the definition of the escrow struct, the definition of the state that this blueprint provides. Now, every single component that we instantiate from this escrow blueprint is going to hold this kind of state. So every single component is going to have access to the state, and the blueprint defines the type of the state. So it's got vaults. It's also got obligations, an obligation non-fungible resource. As I told you, every single party in this exchange or in the escrow is going to be given an obligation NFT. It defines the obligations that this party has and defines the tokens that it should get out. This is the resource address of that NFT, and we're mainly storing it in our component state because we will need to validate the proofs that we get against this resource address. We'll need to make sure that people are providing us with a proof of the correct NFT. We'll get into that in a little bit, but yeah. Finally, we've got this one more state variable. It's called is escrow fulfilled, and it's a boolean, and essentially we can say that an escrow has been fulfilled once both parties have paid the tokens that they are required to pay to the escrow. So this is when we can say that the escrow has been fulfilled. So let's get into the functions that we have here, and now we're gonna be beginning the live coding in a moment. Is escrow fulfilled? I don't want to get into too much detail into this method or what it does, but high-level overview, it checks if the vault contains the resource specifier amount, and if it does, then it says, then yes, this vault has been fulfilled because the amount that we were contracted is actually inside of there. If it isn't, then it says no, the escrow has not been fulfilled and people are not allowed to withdraw their tokens. So let's actually begin doing the live coding, and let's actually begin writing this code. I'm gonna expand this since we'll be using it. The first function that we have is called instantiate escrow. The instantiate escrow function that we're going to be writing right now is a function on the blueprint that creates new escrow components for us. It takes two arguments. The first argument is the amount to be paid by the first party, and the second is the amount to be paid by the second party. Based on that, it will create the new obligation resource for us. It will mint the NFTs for us, and it will then instantiate the new escrow component for us that has the vaults that people can deposit funds into. And so this is the sort of thing that this function will do. So let me remove this and let's begin with actual coding. In the docstring, you'll see that this function is going to be doing some checks. And the way that I usually like to do it is to include all of my checks and assertions at the very beginning of the function body or the method body to say, assert that this is true or assert that this is not true, and then after all of the assertions and checks and all of that is done, I do the actual logic. So the first assertion is that we would like to assert that the resource specifiers are valid. Like to make sure that these two resource specifiers are valid, and we talked previously about when a resource specifier is valid and when it isn't. So I'll begin with an assertion statement. I would like to assert that to be paid by party 1, validate. I would like to assert that it is okay, that the validation is completed successfully. And let me include a user-friendly error message in here. Maybe something like first resource specifier is not valid. I can also copy this, put it right here, and I can validate the second resource specifier. So now I've performed the validation of the two resource specifier. We performed it through the validate function, or the validate method that I have defined on the resource specifier enum, and we talked previously about what exactly it does and the types of validation that it does. High level overview again and a quick summary. It makes sure that the amount of fungible tokens specified is greater than or equal to 0, and it also validates that the non-fungible IDs, that there is at least one or more non-fungible IDs provided for non-fungible tokens, like a name and the name, and perhaps we could also have a description. Description could perhaps be this resource describes the obligation of the two parties involved in the exchange. So you can put any description that you would like. So with this, let me just remove this no initial supply. I would like to have some initial supply, and the initial supply, the sort of format expected for it is that it is an array of tuples. The first item in the tuple is going to be the non-fungible ID of that NFT, or it's going to be a reference, or no, not a reference, sorry. It's going to be a non-fungible ID of the NFT. I would like my very first NFT to have an ID of 1 and to have this type of data. Let me format it differently. I would like my second NFT to have an ID of 2 and to have this data. So again, let's take a look at what exactly we're doing here. We are creating a new resource, and this resource is going to be a non-fungible resource. We're specifying some metadata on this resource, and we're specifying an initial supply. The initial supply is going to be 2 NFTs, and it's defined in an array of tuples. The first NFT is going to have an ID of 1 and is going to have this data, party 1 obligation. The second NFT is going to have an ID of 2 and is going to have a data of party 2 obligation. And so this is what the second NFT is going to have. All right, fantastic. So now that we have done that, what else do we need to do? Create the escrow obligation resource and mint the 2 escrow obligation NFTs. This is done. Instantiate the component based on all of the above operations. Fantastic. So I think that we're actually ready to instantiate our component. So let's see. What exactly do we have? So when we instantiate our component, we will need to provide all of this state. The obligation non-fungible resource, we've just created that, so we've got this available. Is escrow fulfilled? Obviously, when the escrow is first created, it's not fulfilled, so this is false. So now we get to vaults. We need to define this mapping of vaults with the 2 resource specifiers that we have and vaults of these resources. We haven't done that yet, so let's actually come and do that here. We'd like to create a mapping that maps the 2 resource specifiers passed to us as arguments to the vaults that will contain resources of this resource specifier. So I'll define a new B-tree map of resource specifier it maps a resource specifier to a vault. And this is a new B-tree map.new. In here, I'll do an insert vault. Sorry, I would like to call this vaults. Vaults.insert a key and a value. The very first key that I will have is going to be the first argument that was passed to me, to be paid by party 1. And I will do a clone of that. And let me just separate this into multiple lines. And the value is going to be a vault new. And when you create a new vault, it asks you about the resource address that it is going to store. Now, I want you to recall one of the things that we talked about during the presentation. We said that a resource container can only contain a single resource address. And when I explained that to you, I said, so you can have a bucket of XRD, another bucket of Bitcoin, and let's say another bucket of ETH. But you cannot have a bucket containing XRD, Bitcoin, and ETH. Same thing with vaults. We need to specify the resource address of the resource that will be stored inside this vault, because it will be permanent, and this will be the resource that the vault is always going to have. So in here, I can say that the resource that this will have is the resource that will be paid by party 1. It's exactly the same resource address. So to be paid by party 1, resource address. I can do the same thing for the second party. So I will insert a new entry into that mapping. I'm inserting the resource specifier and a new vault. The vault is going to be of this resource that is to be paid by the second party. So now that we have all of this, we are actually ready to instantiate our component. So I'll say component address is equal to self. And when I do this, I need to specify the vaults. What else do I need to specify? The obligation non-fungible resource, the resource address of that resource. So that will be my escrow obligations dot resource address. And then I also need to specify, is escrow fulfilled? When the escrow is first instantiated, it is not fulfilled. Then I will do dot instantiate and dot globalize. And once I have that, my function here, it returns a tuple containing a component address and a bucket. The component address is of the newly instantiated component from this function, and the bucket is of the obligation NFTs that we've just created. So I will return my component address and I will return my obligation NFTs. And this is it for the instantiation function. So let's again take a look at what exactly we've done so far. We wanted to define a method on our escrow blueprint, and we wanted this method to be used to instantiate new escrows for us. When you're instantiating or creating a new escrow component, you're sort of defining the contract between the two parties. You're saying that this is the amount that party 1 is going to pay, and that is the amount that party 2 is going to pay. You're sort of you need to specify the contract that sort of exists between these two different parties. When we do that, we'll be returning a component address and a bucket. The component address is going to be of the newly created component, and the bucket is going to be of the obligation NFTs that we created. And again, if you recall, we talked about this earlier. The obligation NFTs are the NFTs that define the obligation that each party has. We did a number of assertions or a number of checks at the beginning of this function. And to be clear, if one of those assertions fail, then the execution is going to fail and the whole transaction is going to fail. We did these checks mainly because I've defined them here for us in the docstring, and these are checks that are typically good to have to make sure that things actually make sense before this escrow component is created. Once we performed these checks, we created the two escrow obligation objects, the escrow obligation objects define the obligation and rights that each of the two parties have. It defines that this is the amount that the first party needs to pay, and that this is the amount that the first party should get. It also does the same for the second party. And we then created a new non-fungible resource of this data. With this, we created a new mapping of resource specifier to vaults, and we created two vaults that will be used to contain the two types of tokens or the two types of resources that we will be putting in our component, and we instantiated our component. We then returned everything that we needed to return, which is the component address and the escrow obligations. So this is what the instantiate escrow function does. So let's now implement the deposit function. The deposit function is meant to be used by the two parties exclusively. Nobody else is meant to be able to use this deposit function. And it's meant to be used by them when they wish to deposit their funds. They are now ready, they've got their funds, they wish to deposit it into the escrow, so they use the deposit function. The first party goes in and says, I've got my funds, I will be providing them to the escrow. The second party goes and says, I have my funds also, I wish to deposit them and provide them to the escrow. And one of the things that we wanted to do is that we wanted the obligation badge to be used as the main method of authenticating and authorizing the two parties. And so when they're calling the deposit method, they need to provide a proof of their obligation badge. Once we have that proof, we'll be able to interrogate the proof to get useful data, to get some of the useful data that it has, and to get the amount that needs to be paid and all of that, but we'll get into that later. So one of the arguments is the obligation badge, and another argument is the funds that they wish to deposit into the escrow. This method returns a bucket, and the main reason why I wanted it to return a bucket is to explain to you how we deal with excess tokens that are sent to us. So I'm mainly returning a bucket for the case that somebody comes in and deposits more funds than they should have. Somebody comes in and says, I will be depositing 200 XRD, but they only needed to deposit 100 XRD to fulfill their part of the escrow or their part of the contract. And so this bucket here returns the change back to the caller, the change that has not been deposited into this component. This method takes a mutable reference to self, and once you see a function or some callable that takes a reference to self, it means that it is a method. It means that it is defined on a component. It requires access to the state. And since this is a mutable reference to self, it means that it requires write access to the state. It can mutate and modify the state, and this is why it needs a mutable reference to self. And the kind of state that it will able to mutate and change is going to be the state of the vault. We'll be depositing funds into the vault, and therefore the state of the vault is going to change. And this is why we need that mutable reference, because the state of the vault is going to be changing. So with all of that out of the way, let me just collapse this, and let's get into the actual implementation. So what we want to implement is a way for people to deposit their funds into the escrow, and we want to authenticate them using the obligation badge that they are providing us. So as always, the very first thing I would like to begin doing is to perform the checks required that we need to perform. So the very first check is that check that the past obligation badge resource address matches the obligation non-fungible resource stored in the component state. So we need to make sure that this person has passed to us a correct obligation badge. They haven't passed to us some resource that they created. They've passed to us an obligation badge that we have created, that we can trust because we've created it. The way that we do this is by validating that proof, and we've got this very easy way to validate the proof. So I'm going to say let obligation badge be a validated proof, and it will say that this is equal to, to obligation badge dot validate proof and I would like to validate that the resource address of this proof is the expected resource address, which is obligation non-fungible resource. And if this check fails, then do this: invalid badge provided. So with this, I have validated that the obligation badge that was passed to me is an obligation badge that we have created ourselves and that we can trust, since we've created it ourselves. So with this out of the way, let's actually get the data on this badge. I told you that every single NFT has some data, and the obligation badge is a proof containing an NFT, and it does definitely have data. So let's load the obligation data stored in this badge. So let obligation be the escrow obligation. That will be the obligation badge, the non-fungible, and I will get the data that is on the non-fungible. So once I have that, there was one more check that I need to do. Check that the funds passed in the bucket match the resource address that is required by the obligation NFT. What do I mean by that? Let's say that in the original agreement, you agreed to pay 200 XRD. But instead of coming to me with 200 XRD, you come to me with 200 Doge. You present the correct obligation badge, and you present me some funds, which is not the funds that we agreed to. You agreed to 200 XRD, but now you're giving me 200 Doge, which is the incorrect funds. I initially said, well, let's do a check to make sure that this that the resource is actually correct. But I'll tell you a little fun fact. The Radix engine can actually catch this for you. And it does this through one of the properties that we talked about earlier. Remember when I said that a single resource container can only hold a single resource address? It means that if we try to deposit as an example, 200 Doge that we did not agree to into the XRD vault, which is what we agreed to, there will be a runtime error and the deposit is actually going to fail. And so we do not need to have an explicit check for that. It can just be an implicit check. We can just try to do it, and if the Radix engine allows for it, then it is allowed. You're trying to deposit the correct amount of, or the correct type of tokens. If it fails, then you're not depositing the correct tokens. You're trying to deposit a different resource from a different resource address, and therefore it fails. And so I will be skipping this mainly because we don't actually need to do it. The Radix engine is going to be doing it for us. So once this is done, we've got the obligation badge and we've got the obligation. Let's now get the vault that these funds are going to be put in. And we'll do that by saying let vault equal to a mutable reference to a vault. It will be self.vault. If you remember, vault is the mapping that maps a resource specifier to a vault, a resource specifier of how much or how many resources the vault is meant to contain to the actual vault. So I'll get mutable. And what I wish to get is the resource specifier of the amount that this party needs to pay. So it was called amount to pay. Of the amount to pay, and then I will unwrap this. So again, what exactly am I doing here? I need to get a mutable reference to that vault to be able to deposit my funds into the vault. The way I go about doing this is by going to the mapping that contains the resource specifier to vault mapping, and I say I would like to get the corresponding vault or corresponding value with this key, and the key is the amount that we need to pay. and then I unwrap, and this is a Rust thing, meaning that this operation could potentially fail if the resource specifier is not actually defined on that mapping. So once I have this vault, there is a little something that I wish to do. Remember when I told you that some people could send us some funds in excess? Some people could, again, they need to pay 100 BTC, but they pay 200 and they expect to get 100 BTC back in change. Well, we need to create a new bucket containing the amount of funds that we will actually deposit into the vault. The way that I will go about doing this is by having different branching logic depending on whether the amount to be paid is fungible or non-fungible. So say funds to deposit. It is a bucket, and it will be equal to some expression. Expressions are a special feature in Rust. Essentially, you can have an expression, and the return of that expression is going to be the thing assigned to that variable. So what I'm going to match is the data on the obligation NFT, and more specifically the amount to pay. If you find that the amount to pay is some fungible resource, then we'd like to get the amount of that fungible resource. And we will create a bucket of this amount. If we find that it is a non-fungible of some non-fungible IDs, then I will do funds.take non-fungibles of the non-fungible IDs, and I believe that this needs to be a reference to those non-fungible IDs. Again, what am I trying to do here? I'm trying to get the actual bucket that we will be depositing into the vault. I'm trying to get the amount that this person is meant to pay. And if they provide any amount in excess, or they provide any additional amounts, I wish to return that to them after the execution of this method finishes. And all I'm trying to do is just to get the funds that I'm actually going to deposit. This requires some branching logic because we'll be dealing with this differently if it is a fungible token, and we'll be dealing with it differently if it is a non-fungible token. And so once we have this bucket, everything else is going to be easy. We will do vault.put the funds to deposit. And once we put the funds to deposit, we can return the funds bucket back to the caller. And the funds bucket that is returned back to the caller is going to contain the remaining funds that we did not deposit. So we spent a little while coding this method. Let me do a quick recap of what exactly we did. The deposit method is meant to be used by the two parties when they have their assets and they are ready to perform the exchange and deposit them into the escrow. It takes the obligation badge that is given to that party, and it takes a bucket containing the funds, and it returns a bucket. The returned bucket is meant to contain the excess amount of tokens sent. If there's no excess that is sent, then this bucket is simply empty when it is returned. As soon as this function begins, it begins by doing some validation and checks. It checks that the obligation badge is a valid obligation badge, that it does have the correct resource address, that it is an obligation badge that we have created. It isn't some badge that somebody else created and is trying to pretend that it is a correct badge. Once we did that, we're able to load the data that is on the NFT in that badge, which is the escrow obligation data. Based on the escrow obligation data, we get the corresponding vault that this party is going to be depositing the funds into. Then we do some branching logic to only take the amount that is required to be paid and to leave out any other amount in that bucket. We take it out into a new bucket called funds to deposit. Once this bucket is created, we put it in the vault. Then we return the original bucket, which will contain the excess amount of funds that were sent to this method. So this is what it does. So we've got one more method that we need to code, and this method is going to be far easier than all of the other methods that we've coded so far, which is the withdraw method. The withdraw method functions in exactly the same way that you expect it to function. Once the escrow has been fulfilled, both parties have deposited the tokens that they need to deposit. The parties may now exchange their tokens by withdrawing the other party's tokens from the escrow. They do that by calling this withdraw method on the component. So let me expand the doc string from here, collapse this doc string, and sort of walk through the sort of checks and logic that this will be doing. The first check is that it will check that the escrow has been concluded and fulfilled. It will make sure before anything is withdrawn, this method will make sure that all parties have paid the amount of tokens they needed to pay, and the escrow has been fulfilled. It also checks that the past obligation badge's resource address matches the obligation non-fungible resource stored in the component state. Again, we need to make sure that the past obligation badge is a valid obligation badge, exactly the same as the previous method. Once we're done with all of these checks, we'll do some actual logic in here. The logic is going to be very simple. From the badge, we will load the escrow obligation data. And then, based on that, we will take all of the funds out of the amount to get vault and return it back to the caller. So it's very simple steps. So let's see what these checks are. Let's begin by implementing the very first check, or implementing the two checks, and then implementing this logic. The very first check is that it checks that the escrow has been concluded and fulfilled. We can do that through calling this. Assert that self dot is escrow fulfilled. Assert that it is true. If it isn't, then we provide them with a user-friendly error message. You cannot withdraw your funds unless the escrow has been concluded. So I provide them with this error message. The other check that we need to provide is that we need to check that the past obligation badge's resource address matches the expected resource address. We've done that in the previous method by creating a validated proof from the proof. So I'm not going to rewrite this again. I'll just copy it and paste it. Okay, once we've done that, let's actually see the kind of stuff that we need to do. We've now done all of the checks. We need to load the escrow obligation data in the past NFT. So we've done this before as well. Let's get this part of the code. So this part of the code loads our obligation data from this obligation badge that has been passed. And now that we've done that, let's actually get the vault that we will be withdrawing the money from, or that we will be withdrawing the funds from. And what I'm thinking is maybe I can actually do this in one step, or you know what, no need for one step. I'll say that vault is a mutable reference to a vault. So this is very similar to what I did up here. I could even copy that code, but I don't need to. I say this is equal to self.vaults.get the obligation.amount to get.unwrap. Once I do that, I can just say vault.take all, and this does it for me. Let me see what this is saying. Oh, sorry, this needs to be a get mutable. Get mutable. Meaning that this vault can actually be mutated and funds can be taken out of that vault. Yeah, right. So I get the vault containing the amount that I will be getting, or that the caller is going to be getting. I then take all of the funds out of this vault and return it back to the caller in a bucket. And so with this, we've actually implemented all of the different functions or methods that we needed to implement on our escrow blueprint. And now we have a fully functioning escrow blueprint. So what I would like to do now is to actually test my escrow blueprint to make sure that it works in the way that I expect it. So the way that I do that is by, let me just open up a new terminal. And I'll be using some of the tools provided to me when I installed the Scrypto toolchain. And these are tools like the Resim or the Radix engine simulator and the Scrypto CLI tools. These two tools can be used hand in hand to simulate how components and blueprints will be run on the network, and to also build and test the actual code. So I usually like to begin anything that I do by doing a resim reset. I'm essentially resetting the state of the simulator, resetting the ledger that the simulator is using, and saying just dump all of that out. I'm beginning from a completely new ledger. Let me clear that. For the purposes of the tests that we'll be doing, I'll be creating two accounts, and these two accounts will be given the two will be the two parties involved in the escrow. So let me do a resim new account. I've created the first account, and I've created the second account. And these are all of the important things that you need to know about your account. For ease of use, I would like to export all of these different things as environment variables. The reason why I'm doing that is because we'll need those in a little bit to be environment variables. We'll need those to be available to us as environment variables for the transaction manifests. So I'll be exporting those. For my first account, I'll be exporting that as an environment variable called account1. For the private key of the first account, I'll be exporting that as priv key1. Same thing for the second account. I'll export account2. And the private key of this account, export priv key 2. So now that I have these as environment variables, let me see if I can actually print them to my console, just to make sure that they worked. Account 1, that works. Account 2, that works. Priv key 1, that works. Priv key 2, that works. Now that I have these, I am free to just clear out my console, and yeah. So now what I would like to do is to set the first account that I created as the default account, meaning that this will be the account that Resim is going to be using. Resim set default account. The first argument, or before I do that, let me show you something cool about Resim. If there's ever something that you do not know about Resim, just put in the Resim and the subcommand and say help. And it will give you a bit of a description of what this subcommand is meant to be doing. So set default account sets the default account, expects a component address as the first argument and a private key as the second argument. So with this information in mind, let me actually try this out. Set default account. It says that it expects a component address as the first argument, which will be my environment variable in account 1. And then it says that it expects a private key in the second argument, which will be priv key 1. And with that, I have set my default account as being the first account that I created. And this is sort of important to tell Resim which account we're going to be using and which account is going to be paying the fees, is going to be having the tokens deposited into it, and so on and so forth. Now that I have this, I want to create two tokens I'll be using these two tokens as the tokens that I'm going to be doing in the escrow, that I'm going to be using in the escrow, or the two tokens that are going to be escrowed out. So resim actually provides us with a very useful subcommand to do that. So let's take a look at which subcommand is that. If I do resim help, I'll see that there is a subcommand called new token fixed, creates a token with a fixed supply. So let me type this out, new token fixed, and I'm going to keep the help the help flag in there because I want to see more information on what this accepts and the types of arguments it expects. The first argument that it is expecting is a total supply, and then it's expecting an optional description if we would like, an optional icon URL, an optional name, and an optional symbol. All right, so we know the types of arguments that this subcommand expects. So let me create our new token. I'll say resim new token fixed. So the first argument that it expects is the total supply of the new token that we'll be creating. I'll be creating a new token with a supply of 1 million. So 1, 2, 3, 1, 2, 3. I'll provide that with a name. I'll call it Bitcoin. I'll provide that with a symbol. I'll call that BTC. Great. So fun fact, I think that this is the very first transaction that we actually ran on our simulator. And this was a transaction to create a new token for us. And this was committed successfully. It ran and was committed successfully. And as a result of this, a new resource was created with this resource address. Similar to what I did with my accounts, I'll be storing this as an environment variable. So I'll say export BTC is equal to this, or sorry, let me say export token 1 as being equal to this. I also want to create another token. I'll be calling that Ethereum with a symbol of ETH. Similar to what I did with BTC, I'll be saving that as an environment variable, token 2. Let me echo those out just to see if they work. Token 1 works, token 2 works, and they have the resource addresses. So this does indeed work. It does indeed work correctly. That's good. Okay. So what we've done so far is that we've created a new account or two new accounts in resim using the resim new account subcommand. We have set the first account as the default account using the set default account subcommand. And then we created two new tokens using the new token fixed subcommand. Fantastic. So now that we've done all of that, one of the little things that I told you is that, remember when I told you that the default account is the account that gets everything deposited to? Didn't we just create two new tokens? We probably have the two tokens that we created deposited to our first account. How do we know that? We can do resim show of the account component address, and this will essentially show us the balances that this account has. So when we see the balances that it has, we see that it has 1,000 XRD. It has a million Ethereum and a million Bitcoin. So we wish to send all of the ETH that account 1 has to account 2, so that account 2 can actually use it when we're actually testing out our escrow. So we'll be using a new subcommand here called resim transfer. So just like all of the subcommands that we've used, let me press enter, or let me do a help to see the kind of arguments that it expects. Resim transfer expects an amount to be provided, a resource address to be provided, and a recipient component address to be provided. So with that in mind, let's try this out. I'll do resim transfer. The first thing that it expects is an amount, which will be a million. It then expects a resource address of the token that we'll be transferring. and a component address of the token of the component that we'll be transferring the tokens to. So we have successfully transferred tokens from our first account to our second account. To verify that the transfer did actually go through and did actually function correctly, let's do a resim show of the first account to verify that it doesn't have any ETH, and it indeed has no ETH. Let's do a resim show of the second account to verify that it does have ETH, and it does indeed have all of the supply of Ethereum that we minted. It does indeed have that. Okay, fantastic. So we've got that sorted out. Good. So we've created our two new accounts, we've created the two tokens, and we've transferred the tokens around and all of that. And I think that we're actually ready now to publish our package to our simulated ledger and to begin testing our escrow. To publish our package, we can use a command called resim publish. Resim publish expects a single argument called path, and the path is just going to be the path of the package that we have, which is this path right here, or this directory right here. It will begin compiling our package for us, and once it's done compiling the package for us, it will publish the package to our simulated ledger, and it will provide us with an address of that package. Recall that packages are addressable, blueprints are not addressable, and so if you want to specify a blueprint, you'll specify that using the blueprint's name. But yeah. So we're just waiting on the compilation to finish. All right, great. So our escrow package was compiled successfully, and we've gotten back a package address from this. Just like what I did with all the previous addresses that we had, I'm going to export that as an environment variable, and I'll just call it package. Let me print it to make sure that it worked. And so that did work. Okay, so now we'll be using our very first transaction manifest, and I've provided them to you here. We'll be using two transaction manifests here. The two transaction manifests are going to be, the very first one is going to first begin by locking a fee and essentially saying I will be locking this fee, I'll be locking this amount of XRD to pay for my fees, and all of the excess amount is going to be returned back to me. We will then be instantiating a new escrow component, and we'll be providing it with a number of arguments to instantiate this escrow with. These arguments say that the first party is expected to pay 20 token 1, is expected to pay 20 BTC, and that the second party is expected to pay 300 token 2 or 300 ETH. And then at the end of all of that, whatever stuff we get back and whatever stuff we have on the transaction worktop, we wish to deposit that into our first account. So let's actually go ahead and run this transaction manifest. I'll do resim run transaction this. Okay, so resim run, the subcommand resim run, ran this transaction manifest for us, and this transaction manifest ran and was successful. At the end of this manifest, there was one new component that was created and one new resource that was created. So what exactly does that mean? Well, if you remember, the instantiate escrow returns a new component address, and it does actually create a new resource. So it tells us that when running this transaction, this new component was created and this new resource was created. I would like to save these two as environment variables. So say export component is equal to this component address, and export obligation NFT is equal to this resource address. Let me now print them out. Echo component, echo obligation NFT. So the environment variables were successful. They did work, and they got exported successfully. And now that I ran the very first transaction manifest, I now want to run the second transaction manifest. And in short, what the second transaction manifest does is it takes one of the obligation NFTs from the first account and sends them to the second account. And this is all that it does. It's not very special. So I'm going to be doing a resim run of the second one. And this was also committed successfully to Ledger. And so now I would like to check to make sure that my first account and my second account, both of them have one obligation NFT each. So I'll do let me do resim show account 1. I see that account 1 has one escrow obligation NFT, and it's a non-fungible, and this is the ID of the non-fungible that it has. Let me check on the second account. It also has one of this NFT escrow, and it's got this ID, this non-fungible ID. Good. All right. So we've created a new escrow. We've created a new escrow component, and we have given each one of the parties their escrow obligation NFT. Now they have that, and now we're actually ready to begin depositing funds into the escrow. Once we're done depositing the funds, we'll try to withdraw the funds so that we can do the exchange, but we'll first begin by depositing the funds. I'll do that by using a subcommand called call method. And I'm mainly using that because we want to call the deposit method on the escrow component. We want to call the deposit method. We want to provide it with our obligation badge and with our funds that we wish to deposit. And so I'll be using call method. And what we see here is that call method requires a component address and a method name, and it takes any variable number of arguments. So let me begin by doing resim call method. We wish to call the component or the escrow component. We would like to call a method called deposit, which is the method that accepts deposits. The first argument to the deposit method is let me see, it's a proof. It's the obligation badge proof. So I can specify that by saying one obligation NFT. The second argument is the funds that we wish to deposit. So the first party is going to be depositing 20 BTC. So that is 20 token 1. So again, I'm doing a call method. I'm calling it on the escrow component. The method I am calling is call deposit. It accepts 2 arguments. This argument right here is doesn't need to be explicitly provided. It is implicit since we're specifying a component. We're calling the deposit method. We're providing it with one obligation NFT, or the obligation NFT that we have. We're providing it with that as a proof, and we're giving it 20 BTC. So let's run that. And we see that the deposit from the first account was successful. It was committed successfully to Ledger. What we need to do now is to switch to our second account and perform the deposit from the second account. So let me do resim set default account. It requires a component address and a private key. That will be account 2 and priv key 2. And so the default account has been updated. Much like the previous one, I'll be using the same call method command. There isn't much that's going to change except for the actual funds that we'll be depositing. We'll be depositing 300 token 2. All right, and the deposit of the 300 token 2s is successful. That did actually work. So by this point here, the first account has deposited, or the first party has deposited its funds, the second party has deposited its funds, all of the deposits are done and completed. Let's now withdraw the funds to see if the exchange actually worked or not. So the way that I would go about withdrawing the funds is, again, another call method. So resim call method. The method I'll be calling is on the component address in the component environment variable. I'll be calling the withdraw method, and I would like to pass it with one of the obligation NFT. I need to present to it my obligation NFT badge so that it knows what kinds of funds I am expected to withdraw. And we see that this was committed successfully. This transaction, which withdraws funds, ran and was successful. All right, fantastic. So we've withdrawn the funds of account 2. Let's switch to account 1 of account 1, priv key 1, and let's try to withdraw from account 1. And we see that this also worked. Fantastic. So to make sure that this did indeed work and that we have the expected amount, let's actually see the balances of the two components. I expect that the account component of party A is now going to have 300 ETH. Account 1. It does indeed have 300 ETH from this exchange that we performed. Fantastic. It has all of the remaining Bitcoin that it had. And I expect that the second account is going to have 20 BTC. The second account does indeed have 20 BTC. And so we have finished testing this blueprinting component, and we see that it does indeed work. And by the end of all of this, we were able to exchange our assets. The first party was able to provide Bitcoin. The second party was able to provide Ethereum, and these assets were successfully exchanged. Fantastic, great. So we're actually done with that. So one more thing. The biggest recommendation that I have for you is to always use the resim help command or the resim help flag. It provides you with a lot of details on the actual on the arguments that are expected, on the arguments they need to provide, and so on and so forth. And so it's an incredibly useful thing to have, and it's invaluable. Truthfully, it is very, very valuable. And so this was pretty much it for the live coding session. So now we're gonna do the Q&A. So I'll give you a few minutes so you can scan this QR code. You can go to this QR code and you can put all of your questions in there. We'll take a few minutes off and then we'll come back with the Q&A. I'll see you then. Hello everybody and welcome back to the Q&A. So now we'll be answering any questions that you might have. I've already went ahead and chosen this very first question. If you have any more questions, just feel free to scan this QR code and submit your questions and I'll be answering them now live. So the very first question that somebody has is, does crypto already have ERC20, 721, and 1155 standards? Before answering this question, one very important thing that I first need to talk about is why do these standards exist on Ethereum in the first place? And once we understand that, we can then answer the question with a very simple yes, no, do they exist, do they not exist? So why exactly do they exist on Ethereum? Well, there is one main reason, which is because the EVM only understands one asset, which is ETH, and because the EVM only understands ETH, there is a need for people to congregate together and to implement this, this agreement that any smart contract that implements this type of state, these types of functions, will be considered a token. So all of these different token standards are one effort to get around the limitations of the EVM only being able to support one single native asset, which is ETH. And so this means that if you have a platform that does not have this limitation, as in if you have a platform that can support many, many, many different native tokens, you do not need these different standards. So to circle back to Radix and Scrypto, do we have these standards? No, we have a platform where anybody can create a token, where tokens are native to the chain, where the chain actually understands all of these different things natively. Meaning that you do not have to implement a smart contract that describes the idea or notion of an asset or of a token or all of these different things. None of these need to be implemented by you, and these are things that are just implemented at the platform itself, and they're understood by the platform itself. And so this is the answer I have to this question. The other question that we have is, can ERC 4907 rental NFTs be implemented in Scrypto? Yes, yes. And this actually relates to the idea of proofs. And let me actually go back to the presentation here. This actually relates to the idea of proofs that I talked about right here. So how can you use this idea of proofs in doing rental NFTs? Well, you can do something really clever. You can say, I'm going to put my resource or I'm going to put my NFT in some component. And if you want to rent it out, you come in, you pay me some XRD, and I give you a proof of owning that resource. I never hand it to you. The actual resource lives in a component that I control, and it never gets handed to you. All that I give you is a proof after you have paid me the amount of money that I wanted you to pay me, and with this you can sort of rent out my NFT if you want. And maybe you can do some more interesting stuff, like saying you pay me some amount of money and then you don't have to pay me for the whole month, and then at the end of the month you have to pay me back, or you can no longer generate a proof from this component that I control and from this resource that I create. The biggest advantage of this is two main advantages. The very first advantage is there's no new token standard that was needed. all of the little Lego bricks available to you in the actual platform made it possible to do something like this without needing an entirely new token standard to do something like this. The second advantage is that you control the component, you control the actual ownership of everything, and so you are in control of this whole of this resource, and you can at some period of time you can say, I don't want it to be rented out anymore. I am done with this, and you can just recall it and take it back. So there are many different advantages to this kind of approach. So quick, simple answer to your question. Can it be implemented? Yes, in a more asset-oriented way, and in my opinion, in a better way. So let me go back to Slido here. All right. Thank you so much for this question. The other question that we have is, within the same transaction, can I create a proof can I create a proof of my XRD, send those XRD, and still present that proof to a component? Or is that automatically invalidated? So this is, by the way, a fantastic question. Really, really, really nice question. So there is something that happens underneath the hood that I didn't tell you about, which is buckets and buckets and vaults have this idea of liquid and illiquid amount. And what this means is that, let's say that you have a vault that has 1 million XRD, and you create a proof of 1,000 XRD from this vault. The 1,000 XRD is now illiquid. This particular 1,000 XRD cannot be withdrawn. The remaining liquid amount can be withdrawn. The illiquid cannot be withdrawn. So in this specific case, can I have a bucket, create a proof from that bucket, send the bucket, but still have the proof? The answer is no. You cannot do that. Why am I unable to do that? Because once you create a proof from a bucket, the bucket becomes illiquid, cannot be deposited, it cannot be moved around, and all of these different things cannot be done. And so this is why something like this is not going to be possible, mainly because of liquid and illiquid amounts. So yes, it is impossible. So, see? Does crypto handle decimals internally like Solidity with 18 decimals, for example? Yes, we do have our own decimal and precise decimal types. The decimal type is an 18 decimal point precision type, and so you have all of these different things natively available to you in Scrypto. No need to re-implement that. No need to go back and do all of these things manually. All of these different things are actually implemented for you in Scrypto. So, what benefits I get from holding tokens in my account natively? Many different advantages. Maybe I can speak about one advantage that I actually think is a really big advantage, which actually relates to decentralized exchanges and how they work. And so if you look at the Ethereum world, every single decentralized exchange has this notion of a virtual balance. And why do they have this notion of a virtual balance? It's because in Ethereum, anybody can send you tokens without you having the power of saying, yes, I want to accept them, or no, I do not want to accept them. And maybe you hear this and wonder, somebody's sending me tokens and I would say no? Why would I ever do that? Well, there is a really good reason to say no to tokens when it comes to decentralized exchanges and liquidity pools. If somebody sends you tokens to a decentralized exchange, to a liquidity pool, without you saying yes and without you accounting for these tokens, it messes up the balance of that liquidity pool, and it sort of messes up with the actual mathematics that happens inside of the liquidity pool. And so unsolicited sending of tokens to liquidity pools in Ethereum could result in the actual math being messed up for that liquidity pool. And so you put some amount of tokens in to exchange those, and you get an incorrect amount of tokens out because the pool is imbalanced. When you have tokens natively inside of your account or inside of your component, you get a say of, do I accept these tokens or not? So you might ask a question, well, why am I unable to do that in Ethereum? Well, in Ethereum, tokens are essentially one big Excel sheet. You don't get to say yes or no on what kinds of things happen in that Excel sheet. It just happens. And so if somebody wants to send you tokens, all that they have to do is just modify this Excel sheet, and that's about it. So you don't get to say yes or no. if we were to implement this decentralized exchange in Scrypto, you would get to say yes or no to these tokens, and you would get to actually account for them. And so this is one of the biggest advantages why it's really good to actually be able to hold these things inside of your account instead of having them in some ERC token that functions more like an Excel sheet, really. So that is the answer I have to this question. So, one, can I cancel the transaction once you deposit funds into the escrow when the actual exchange takes place in the moment of the second required deposit? So, being able to cancel escrow transactions, I did not implement that into this blueprint. However, if you wanted, you can actually do something like this. You can build a really clever timed system, and you can have something clever that maybe says, this escrow is going to happen from this epoch to this epoch. And if we get past this epoch and one of the parties hasn't paid, then the other party can withdraw its funds. Or you can code it in a different way to say, once you deposit, you can withdraw your funds if the other party has not deposited. You can do all of these different things. In my implementation that I showed you today, I did not implement any of this. I mainly did not implement them just because I wanted this blueprint to be simple, and I did not want to overcomplicate how this blueprint worked. So yeah, but the answer to your question, this can be implemented, but I did not implement it today. So yeah. Can you describe a bit how fees work? I heard they can be handled directly by component, but how? Does the component need to hold XRD to handle those fees? Really, really good question, really interesting question. So to answer the second part of your question, can a component, so let's say that I have a component and somebody makes a big transaction in my component. And maybe I want to say, look, you've made a really big transaction. I want to pay your fees. I'll be paying your transaction fees for this transaction. Can I do that? Yes, you can absolutely do that. And you can actually do this in a really clever way. And we call it lock fee or something like that. Or lock contingent fee, that's the name. And lock contingent fee, what it does is that it says, if the transaction succeeds, I pay your fees. If it doesn't succeed, I don't pay your fees. And we're essentially doing this just to limit what people can do. We don't want people to come in, make a big transaction, get that component to pay the fees, and then make that transaction fail. So what you can do is that you can say, me as the component, I will be paying your fees in the one condition that the actual transaction succeeds. If the transaction does not succeed, I don't pay your fees, you pay your own fees. So this is one of the things that you're able to do with Radix. Have components pay fees. Can you describe a little bit how fees work? Just as a very high level overview, at the very beginning of every single transaction, what you do is that you lock a fee. Essentially, you say, I have 10 XRD, I will be locking my 10 XRD for fees. So this will be the 10 XRD used to pay for fees. And when the transaction finishes, if any of the 10 XRD is remaining, it goes back into my vault. If none of it is remaining, if all of it is, or let's say, if all of it was consumed, that's fine. If all of it was consumed and there are still instructions that we need to run, then this transaction is going to fail, mainly because all of your fees have been consumed. All of the fees that you have locked or the XRD that you have locked has been consumed, but the end of the transaction was not reached. And so, yeah, that's one of the things. So somebody is asking how to learn more past this introduction. So there are multiple different ways of actually learning more about Scrypto and going in deeper and deeper. And I'll tell you about my personal favorites, and I think that this is going to be very different for different people because different people learn in different ways. Me personally, I learn best by example. If I have some example code that I can see, this is the best way for me to learn. And this was one of the main things that we have with Scrypto. We have two main repositories filled with examples, filled with many, many, many useful examples that you can go through and read. And all of these examples are open source. And some of these examples have excellent documentation that you can read to understand what exactly they do. And we have a lot of, let's say, real-world applications or really useful applications. We've got examples for decentralized exchanges, NFT marketplaces. We have examples for stuff like OpenZeppelin's payment splitter. We've got examples for escrows. We've got examples for vaults that use really interesting access rules that not everybody is able to withdraw from. We've got many different examples that you can find, and this would be, in my personal opinion, the best way to learn. But again, it depends on you as a person and on how you prefer to learn. So the two examples repo, I'll be sure to provide them to you. If you would like, just message me on Discord. I'll provide these to you, or I'll get them to you in any way I can. The second way to learn would probably be to read the documentation. We've got excellent documentation on all of the different aspects of Scrypto, or at least most of the different aspects of Scrypto. So reading documentation would be also an excellent way to learn. If you're looking for more introductory stuff, webinars like these and presentations like these happen quite often, and they could be a good way for you to sort of gain information on Scrypto and to understand Scrypto even more. And if you reach a point where you feel confident, you can join the challenges that we do. And so these are the main ways of learning. So, yeah. So this is done. Are buckets ephemeral, or do they persist afterwards? Can they be reused for more than one transaction? So buckets are meant to be purely for the period of the transaction, for one transaction. They cannot be reused after a single transaction. So they are ephemeral, they are not permanent, they are not persistent. The persistent storage of resources is called vaults, and vaults is the is stored inside components, and they're persistent and they go nowhere and cannot be moved. And so a bucket can only be used for the inside a single transaction and cannot be reused again. And I don't imagine that there are many use cases for reusing buckets, but if there are, I would love to hear about them. So, yeah. So, how do buckets and vaults hold assets from other blockchains? So, buckets and vaults, if you wanted to hold assets from other blockchains, you'd go down the route of bridging those assets or having a wrapped version of those assets. And maybe this comes, and perhaps I think that what you're referring to is when I said a bucket of BTC, ETH, and XRD. When I said this, this was purely an example. I'm not saying that you can have these native BTC inside of your vaults and buckets. This was purely an example that I gave. And so if you wanted to hold these assets inside of your vaults and buckets, you would most likely have to pass through a bridge, and the bridge is going to wrap these assets in a representation that is understood by Radix and that is understood by Scrypto, and then you'd be able to have them in your buckets and vaults. So not directly, and I think that this is mainly referring to the example that I gave. You can't have that happen directly. You need to wrap them. So, yes. And so, so somebody is asking, I am looking for potential project partners. Where do I find them? There is a channel in our Discord. It's called Looking for Teammates. If you're looking for teammates, you've got this idea, you'd like to build something, you can go to that channel, you can post about the kind of skills that you have, or maybe you can find somebody, you can message them directly. But there is one main channel called Find a Teammate on our Discord, and this would be the main way for you to find teammates, or you can go about finding teammates in a different way. And so, yeah. All right, so this will be the last question for today. Can the escrow communicate to both parties that the deposits have been done? So the way that this would typically happen would probably be through an indirect way, perhaps some kind of Boolean value on the NFT that says the escrow is completed, come withdraw your assets, something along the lines of that. Or this could also happen as an off-chain thing of an off-chain service communicating to both parties that the escrow has been done. And so the way that I would personally go about implementing this, if I was building a real-life escrow, I would probably just have a Boolean value on the NFT saying, is escrow completed? And once the escrow is completed and both parties have paid, this gets updated so that when you open your wallet or when you open an Explorer, you see that, okay, I see that this has been, that both parties have paid and that both parties have finished, and it becomes very clear to you. And so, yeah. So this was all the questions that we had during today's presentation. If you have any more questions, please just drop them in the Discord, and I'll be very, very happy to answer your questions if there are any. I'll personally be in the Discord after this presentation, so if you have any questions, feel free to do that. So let me go back briefly to the slides here. Let me remove this, and let me go back to the slides, and let me actually scroll down here. All right, so thank you so much for attending this presentation. Here is a number of closing remarks. We will be doing a challenge today, and the challenge for today is going to be to build the same escrow blueprint that we built during this presentation. There is a slightly different challenge between people attending in person and people attending online. I believe that everybody should have received emails with the instructions. If you haven't received them already, here are the QR codes. Scan the QR code that is right for you, whether you're attending in person or whether you're watching this online. Just feel free to scan the appropriate QR code for you. As I said, the challenge is to build the same escrow blueprint that we built today. However, you are not going to be starting from scratch. You're going to have some boilerplate code. You're essentially going to be beginning from the same place that I began from during this presentation. And to be very clear about this, this isn't meant to be a complicated challenge or anything, and I would very much love it to see people actually collaborating on this, sharing code, sharing ideas, and so on and so forth. And so this isn't meant to be something very secretive where you do something and never share it. You're meant to share this, you're meant to try it out, and you're meant to collaborate with other people on this challenge. And it's very highly recommended that you do so. And so again, if you haven't scanned your QR code already, or if you haven't received the challenge instructions, scan the appropriate QR code for you, and we hope to see you during today's challenge. If you enjoyed this presentation, I would really recommend that you join our Discord. I am personally going to be in the Discord after this presentation finishes, answering any questions that you might have, talking and discussing different ideas, and also helping you out in the challenge. As I said, the challenge isn't meant to be complicated or anything. It's meant to be an opportunity for you to try Scrypto out. So I'll be in the Discord helping you out in the challenge if you need any help or anything. So feel free to join our Discord. We also have a developer program where we update people on the latest things happening with Radix and Scrypto. Feel free to join our developer program if you find that to be interesting. And yeah. So I think that this about wraps up everything that we had for today. Thank you all for coming to this presentation. I hope that all of you have enjoyed it. I'll see you around in the Discord, and I'll see you later. Goodbye.
da 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 da